Close your eyes and imagine the boundless expanse of space stretching out before you, a vast canvas of darkness and light. Stars twinkle in the distance like tiny beacons in the night, while planets spin slowly in their eternal dance. The silence here is so profound that you can hear your own breath slowing with each passing moment. Tonight, we'll embark on a journey through the depths of the universe, where there's no room for hustle or worry, just the gentle glow of distant galaxies and a peace that wraps around you like a warm blanket, carrying you into a world of sweet dreams. Imagine a stillness so vast it defies comprehension, a quiet so deep it hums in the absence of sound. Before the universe burst into being, there was no time ticking forward, no space stretching outward, no light to pierce the dark. This was the state before the Big Bang, a realm of infinite mystery, where the rules we know simply didn't exist. Picture it like an endless ocean, not of water, but of possibility, its surface undisturbed, waiting in silence. Scientists call this the pre-Bang era, a concept so elusive it slips through our grasp. Yet it holds the seeds of everything we see today, the stars, the galaxies, the very air you breathe. In this tranquil void, there was no motion, no chaos in the way we understand it. Chaos implies something to disrupt, but here, there was nothing to stir. Some thinkers suggest it wasn't emptiness in the usual sense, but a kind of fullness, a potential so immense it couldn't be measured. It's as if the universe was dreaming, curled up in a single, timeless point, smaller than a grain of sand, yet heavy with the promise of all that would come. This point, this singularity, wasn't a place you could visit or a thing you could hold. It was an idea, a whisper of existence, resting in perfect calm. The beauty of this moment lies in its simplicity. No planets spun, no suns blazed, no winds carved distant worlds. Yet within that stillness, the laws of nature as we know them were waiting, folded into an invisible tapestry. Quantum physics offers a gentle hint here. Even in what seems like nothing, there's a flicker of something. Tiny ripples of energy, too small to imagine, might have danced in this pre-universe state, fluctuations so faint they're like the breath of a sleeping giant. These whispers of energy weren't loud or hurried. They moved with a rhythm as soft as a lullaby, hinting at the forces that would one day shape reality. Picture these fluctuations as threads in a vast, unseen web, each one quivering with potential. Some scientists believe they arose from the strange rules of the quantum world, where things can exist and not exist all at once. It's a soothing thought, nothing rigid or certain, just a gentle play of possibilities. Others wonder if this state was tied to a larger cosmos, a sea of other universes floating like bubbles in an endless foam. Each bubble, a universe of its own, resting in quiet harmony, separate yet connected by the same deep stillness. There's no need to choose one idea over another. They all weave into the same serene story of a time before time. What's fascinating is how this quiet nothingness held everything. Every galaxy that would swirl across the sky, every note of life that would hum on a distant planet, it was all there, tucked away in that single, peaceful point. Imagine it as a seed, not of wood or earth, but of pure energy, glowing faintly in the dark. Not a harsh glow, but a soft one, like the light of a firefly on a warm night. This seed didn't rush or strain, it simply was, existing in a state so balanced it could hold the weight of infinity without breaking. And yet, this stillness wasn't empty in the way we might think. Emptiness suggests a lack, a void longing to be filled. This was different, a fullness beyond form, a completeness that didn't need to prove itself. Some theories paint it as a place where gravity, energy, and matter were one, blended together in a harmony too perfect to disturb. Others suggest it was a boundary we can't cross, a curtain drawn across the stage of existence. Whatever it was, it carried a sense of peace, a stillness so profound it feels like the universe was resting, gathering itself for the leap it would soon take. The science here is gentle, not demanding. We don't need to pin it down with numbers or equations, those come later, when the story grows louder. For now, it's enough to drift in the idea of it, a cosmos not yet born, suspended in a timeless hush. The questions it raises are soft ones. Was there a before at all? Or does time itself begin with the bang? Did this quiet point emerge from something else? Or was it always there, eternal and patient? These aren't puzzles to solve tonight, they're thoughts to cradle, letting them float like leaves on a slow-moving stream. As you linger in this image, this endless, tranquil sea of potential, feel the weight of it settle around you. It's not heavy or overwhelming. It's a blanket, warm and familiar. The universe, before it became the vast expanse we know, was a single note, held in silence, waiting to sing. And then, in a moment so subtle it's almost imperceptible, that note began to shift. The stillness stirred, not with a crash, but with a sigh that would unfold into time, into space, into the first flicker of everything. The seed of the Big Bang was ready, and from that calm, infinite point, the story of the universe would gently begin to bloom. From that sigh of infinite stillness, something stirred, a whisper so gentle it barely disturbed the calm. This was the moment when time began to hum, when space unfurled like a flower opening to the first light of dawn. Picture it, a single, perfect point, smaller than the tip of a pin, holding everything that would ever be. And then, with a breath, it released. Not with noise or fury, but with a quiet grace, like a ripple spreading across a still pond. This was the birth of the universe, a moment so vast yet so soft. It cradles the mind like a lullaby. In this fleeting instant, the rules of reality took shape. Time, which had no meaning before, began its steady tick, a rhythm as soothing as waves lapping at a shore. Space, once folded into that tiny seed, stretched outward, a canvas of endless possibility painted in strokes of energy. Scientists mark this as the Big Bang, but there's no need to imagine a deafening roar. Think of it instead as a sigh of creation, a soundless bloom that carried the promise of stars and worlds. The universe didn't leap into being, it flowed, smooth and unhurried, like honey spilling from a jar. What's beautiful here is how everything emerged from so little. That single point wasn't just small, it was dense beyond imagining, a treasure chest of all existence packed into a space too tiny to see. Within it, energy pulsed, not wild or chaotic, but alive with potential. This energy wasn't something separate, it was the universe itself, a glowing thread weaving the fabric of reality. Picture it shimmering, like dew catching the first light of morning, each glimmer a hint of the galaxies to come. There was no up or down, no here or there, only this radiant beginning, resting in perfect balance. The science of this moment is a quiet wonder. In that first heartbeat, far less than a second, a fraction so small it defies our clocks, heat beyond measure filled the newborn universe. But this wasn't a harsh fire, it was a warmth, a glow that bathed everything in possibility. The temperature soared to trillions of degrees, yet there's a peace in knowing it was the cradle of all things. Matter didn't exist yet, not as we know it. Instead, there was a sea of light and energy, swirling together in a dance too delicate to disturb. It's as if the universe was singing its first note, a melody so pure it needed no words. This sea of energy moved with a rhythm all its own. Tiny packets of light, softer than a whisper, darted through the glow. These were photons, the first messengers of what would one day become suns and skies. They didn't clash or hurry, they flowed, like fireflies drifting through a summer night. And beneath them, the forces that hold reality together began to awaken. Gravity, gentle and patient, started its pull. Other forces, like the ones that bind atoms or spark stars, flickered into being, each one a thread in the tapestry of existence. Tushpertut. They wove a harmony so seamless it feels eternal. Imagine this moment as a painting, not yet finished, but already breathtaking. The canvas of space stretched outward, vast and smooth, while time brushed its first strokes across it. There were no edges, no boundaries, just an endless unfolding, a dream taking shape. Scientists measure this instant in numbers too small to hold on to, 10 to the minus 43 seconds. A blink so brief it's more like a sigh. Yet within that sigh, the universe was born. A quiet miracle cradled in the palm of infinity. It's a thought to drift with, letting it settle over you like a warm breeze. And here's the mystery that wraps it all in wonder. We can't see this moment directly, but its echo lingers. The light from that first glow still hums through the cosmos, a faint whisper we can catch with patient tools. It's called the cosmic microwave background, a soft glow that fills the sky, like the memory of a dawn long past. Knowing it's there feels comforting, a reminder that this gentle birth left traces we can still touch. The universe, even in its earliest breath, was already leaving a story for us to find, written in light too faint to startle. As this newborn reality rested in its glow, something remarkable began to stir within it. The space that had just unfolded wasn't content to stay still, it yearned to grow. The energy, so perfectly balanced, held a secret. It was ready to stretch, to expand in a way that would carry it beyond imagining. Like a river finding its course, the universe prepared to flow faster, wider, deeper. This wasn't a rush or a race, but a natural unfolding, as calm as a petal drifting on water. And so, from this tender moment of birth, the cosmos took its next step, easing into a vast expansion that would shape all that followed. As the universe took its first gentle breath, it didn't settle into stillness. Instead, it began to stretch, like a vast sail catching a soft wind. This wasn't a slow drift, but a swift, graceful expansion, unfolding faster than a dream. Picture it, a cosmos so new it barely had form, suddenly blossoming outward, its edges racing into the unknown. Scientists call this inflation, a moment when the universe grew from something tinier than a speck to an expanse vast enough to hold all the stars we'd ever see. It happened in a whisper of time, yet it carried the calm of a river finding its way. Imagine that newborn space, still glowing with the warmth of its birth, swelling in every direction. In less than a blink, far less than a second, a sliver so small it's almost nothing, it grew a trillion times larger. Not with force or strain, but with a smoothness that feels like silk sliding over skin. This wasn't chaos, it was a dance. Each step precise and unhurried, as if the universe knew exactly how far it needed to reach. The energy within it, that shimmering sea of light, stretched thin but never broke, holding the promise of everything to come. What's mesmerizing here is the scale of it all. Before this stretch, the universe was so small you could cradle it in your hand, if hands existed then. After, it was wider than any ocean, broader than any sky, yet still so young it hadn't learned to shine. This rapid growth smoothed out the wrinkles of its birth, like a cloth being gently pulled taut. Tiny ripples in that early energy, those faint whispers from before, were carried along, stretched into patterns that would one day seed the stars. It's a quiet beauty. Knowing the vastness above us began with such a delicate push. The science behind this is soft and soothing. Inflation didn't need loud engines or violent bursts. It came from a kind of energy, something deep and unseen, like a current beneath still water. Some call it a field, a gentle force that filled the universe and nudged it to grow. This field wasn't harsh or demanding, it flowed, lifting the cosmos higher, wider, with the ease of a leaf rising on a breeze. And as it worked, it cooled the searing heat of that first moment, softening the glow into something calmer, something ready to settle. Picture this expansion as a great unfolding, a tapestry of space rolling out across the void. It didn't tear or fray, it simply grew, each thread of energy stretching in harmony with the rest. The universe became a canvas, vast and smooth, painted with the lightest touch of possibility. Scientists say this happened in a fraction of a second, 10 to the minus 36 seconds, a number so small it's more like a sigh than a count. Yet in that sigh, the cosmos found its shape, a shape so grand it would hold galaxies like drops of dew on a web. There's a mystery woven into this growth, a quiet wonder that lingers. Why did it stretch so fast? Perhaps it was the nature of that early energy, restless yet peaceful, eager to explore its own bounds. Or maybe it was a balance, a way to smooth the roughness of the beginning into something even and serene. Whatever the cause, it left the universe vast and uniform, a sea of space so alike in every direction it feels like a perfect calm. Look up at the night sky, and know this moment touched every star you see, stretching their light across the dark. And here's a gentle fact to drift with. This expansion didn't just make space, it set the stage for everything else. Those tiny ripples, stretched thin by inflation, became the seeds of structure. One day, they'd gather into clouds, then stars, then the swirling arms of galaxies. But for now, they were just hints, faint echoes in a cosmos still too young to shine. The universe, in its swift bloom, was like a garden preparing to grow, soil turned, seeds sown, all resting in the hush before the first sprout. It's a thought to cradle, letting it settle over you like a blanket of starlight. As this great stretch slowed, the universe didn't stop moving, it simply shifted. The energy that drove its growth began to fade, melting into something new. The cosmos, now vast beyond measure, cooled further, its glow dimming into a softer warmth. Space itself held steady, wide and smooth, ready for the next step in its quiet journey. What came next wasn't a leap or a rush, but a settling, a moment when that sea of light began to thicken, to hum with the first hints of substance. The universe, still so young, was easing into a new phase, where energy would glow hotter and dance in a plasma of endless possibility. The universe, now vast and smooth from its gentle stretch, glowed with a warmth that filled every corner. This was a sea of light and heat, a shimmering broth too hot to hold form, too alive to stay still. Imagine it, a cosmos so young it hadn't yet learned to settle, its energy swirling like mist over a dawn lake. This was the time of plasma, a radiant, flowing state where the universe danced in its first seconds, bathed in a glow brighter than 1,000 suns. Yet there was no harshness here, only a soft hum, a lullaby of creation unfolding. In these earliest moments, the heat was beyond measure, millions of degrees, a furnace of pure energy. But picture it as a blanket, not a blaze, wrapping the cosmos in a golden haze. There were no stars, no planets, just this endless sea of plasma, a blend of light and power too fluid to grasp. It flowed like a river of molten amber, smooth and unbroken, stretching across the newly widened space. This wasn't a place of solid things, it was a realm of motion, where energy wove itself into patterns too delicate to see, too gentle to disturb. What's enchanting about this time is its simplicity. The universe was a single, glowing soup, made of tiny packets of light and the forces that carried them. These packets, little messengers of energy, darted through the haze like fireflies on a warm night. They moved with a rhythm, not a rush, their paths crisscrossing in a dance that held no beginning or end. Alongside them flowed other whispers, bits of energy that would one day become the building blocks of everything. For now, they were free, untethered, drifting in the warmth like leaves on a slow current. The science here is a quiet marvel. In those first seconds, less than a minute, really, the universe was too hot for anything to hold together. Matter as we know it couldn't form. Instead, there was this plasma, a state where energy ruled supreme. Light couldn't travel far, it bounced and scattered, trapped in the glow like sunlight caught in fog. This made the cosmos opaque, a shimmering veil that hid its own depths. But there's a peace in that thought, a universe so alive it couldn't yet show itself, resting in a cocoon of its own making. Feel the texture of this moment, a sea so dense with energy it pulsed with possibility. Gravity, still soft and new, tugged gently at the flow, while other forces, those that spark stars and bind life, played their own subtle roles. They wove together, not in conflict but in harmony, like threads in a tapestry yet to take shape. The heat kept everything apart, a tender barrier that let the universe breathe, letting it expand and cool just enough to dream of what might come next. It's a scene to drift in, imagining the cosmos as a painter mixing colors before the first stroke. And here's a soothing truth. This plasma wasn't silent. It hummed with a sound we can't hear today, a vibration born from the energy itself. Scientists say these waves rippled through the glow, tiny echoes that stretched with the universe's growth. They were the first notes of a cosmic song, faint and fleeting, like wind chimes on a distant breeze. Those ripples left traces, hints we can still find in the sky's oldest light, a memory of a time when the universe was all motion and warmth, too young to settle into stillness. Picture this glowing sea as a cradle, rocking gently in the dark. It wasn't empty, it was full, brimming with the seeds of reality. Every star that would ever shine, every world that would spin, was tucked within this radiant haze, waiting for the right moment to emerge. The heat was a guardian, holding everything in a fluid embrace, letting the cosmos ease into its next step. There's a beauty in that patience, a sense that the universe knew how to take its time, unfolding its story with the care of a flower opening to the sun. As the seconds ticked on, still so few, yet so vast, the glow began to shift. The heat, once a fierce cradle, softened further, letting the sea of plasma cool into something new. The light that had danced so freely started to slow, the energy thickening like mist turning to dew. The universe wasn't rushing, it was settling, preparing to weave its next layer. From this warm, flowing state, the first tiny pieces of matter began to whisper their presence, gathering like droplets on a window pane. The cosmos, still bathed in its gentle glow, was ready to take shape, easing into a time when the building blocks of all things would quietly form. The universe, cooling from its radiant dance, began to settle into a quieter rhythm. The glowing sea of energy, once too hot to hold shape, softened, letting tiny whispers of substance emerge. Picture it, a vast, shimmering mist, slowly parting to reveal the first delicate threads of matter. These were the building blocks of everything, small, fleeting, yet heavy with the promise of stars and worlds. Like dew forming on a still morning, they gathered gently, each one a spark in the endless calm of the cosmos. This was the time when particles were born, the gentle birth of reality's foundation. In this tranquil expanse, the heat had eased just enough. Where once there was only light and motion, now there were hints of something more. The energy that had flowed so freely began to weave itself into tiny pairs, bits of matter and their opposites, like reflections in a calm pool. Imagine them as fireflies blinking into existence, their glow soft and brief. Some called them quarks, others electrons, but names hardly matter here. They were the universe's first children, drifting through the haze, too small to see yet vast in their potential. What's beautiful about this moment is its balance. For every spark of matter, there was a shadow, an antimatter twin, born in perfect harmony. They danced together, these pairs, swirling in the fading warmth like leaves caught in a gentle breeze. Sometimes they met, dissolving back into light with a sigh, a flicker too faint to startle. But not all vanished. A whisper of matter lingered, a tiny excess that tipped the scales ever so slightly. It's a mystery why, perhaps a secret woven into the fabric of the cosmos. But that whisper would one day become everything we know. The science here flows like a quiet stream. In those first moments, still just seconds old, the universe cooled to billions of degrees, a number too grand to hold, yet softer now than before. This cooling let energy settle into form, guided by the forces that cradle reality. Gravity hummed in the background, patient and steady, while other powers nudged these tiny bits into being. They weren't solid yet, not like stones or dust, just fleeting sparks, too restless to rest, too light to fall. Picture them as seeds, carried on an invisible wind, waiting to take root. Feel the wonder of their smallness. These particles were so tiny they defy imagining, smaller than a grain of sand, smaller even than light itself. Yet within them lay the blueprint of all things, the mountains, the oceans, the air you breathe. They moved through the cosmos, a sea of possibility, their paths tracing patterns too gentle to trace. Some paired up briefly, others drifted alone, all part of a slow, graceful unfolding. The universe was like a weaver at her loom, threading these sparks into a tapestry that would stretch across time. And here's a soothing thought. These tiny bits weren't alone. Light still bathed them, that golden glow from the beginning, though it was dimming now. The photons, the messengers of energy, wove through the haze, brushing against the newborn particles like a soft hand. They couldn't travel far yet, not through this thick, warm soup, but they carried the memory of the universe's birth. It's a comforting image, a cosmos cradling its first creations, letting them drift in a glow that felt like home, a light too gentle to overwhelm. Imagine this scene as a painting, all soft edges and muted tones. The universe, once a single note of energy, was splitting into chords, matter and light playing together in quiet harmony. These particles weren't hurried, they flowed with the ease of a river finding its bed. Some were heavy, some light, but all were equal in this moment, each a piece of the whole. Scientists measure this time in fractions, 10 seconds, 100, but it's enough to know it was slow, deliberate, a pause before the next step. The cosmos was breathing, letting its new children find their place. As the warmth continued to fade, these sparks of matter grew steadier. The sea they swam in cooled further, the light thinning like mist at dawn. They began to feel each other's pull, drawn by forces too soft to rush them. The universe wasn't finished shaping them, it was preparing, setting the stage for something deeper. Those quarks and electrons, so free and fleeting, were ready to join hands, to blend into something new. Like petals folding into a bud, they hinted at the next bloom, a time when these tiny bricks would fuse, crafting the first elements in the quiet forge of the cosmos. The universe, now a cooling sea of tiny sparks, began to weave something new. Those fleeting particles, drifting like petals on a gentle stream, felt a soft pull, a call to come together. Picture it, a vast, glowing haze where the smallest pieces of matter started to blend, fusing in the warmth like droplets merging on a window pane. This was the time when the first elements took shape, simple, delicate threads of substance born in the quiet heart of the cosmos. It was a slow dance, a tender crafting, as the universe painted its earliest colors. In this soothing expanse, the heat had softened to millions of degrees, a furnace still, but gentler now, like embers glowing in a fading fire. The tiny bricks of matter, those quarks and electrons, found each other, drawn by forces as natural as a breeze. They paired and twirled, forming the lightest of elements, hydrogen, a whisper of existence, and helium, its slightly heavier kin. Imagine them as the first notes in a lullaby, simple yet profound, humming through the haze with a rhythm too soft to startle. These were the seeds of all stars, born in a moment of calm creation. What's beautiful here is how little it took. The universe didn't need grand tools or loud clashes, just time, warmth, and a sprinkle of energy. In those first minutes, 3, maybe 10, the cosmos acted like a patient smith, forging these elements in its glowing forge. Hydrogen came first, vast and plentiful, a single spark of matter with a companion of light. Helium followed, a touch more intricate. 2 sparks joined in a quiet embrace. Together, they filled the universe, a sea of simplicity floating in the fading glow, ready to drift into eternity. The science flows like a river here. This crafting, this fusion, happened as the cosmos cooled, letting particles slow enough to hold hands. The heat was just right, not too fierce to tear them apart, not too cold to stall their dance. A few traces of something heavier flickered into being too. Lithium, a rare guest. So faint it's like a shadow in the mist. But mostly, it was hydrogen and helium, the universe's gentle firstborn, making up nearly all that was. They were light as a sigh, yet they carried the weight of all that would come. Feel the serenity of this moment. The universe was a vast nursery, cradling these newborn elements in its arms. Light still swirled around them, that golden haze from the beginning, but it was thinning now, stretching with the cosmos itself. The particles didn't rush or fight, they settled into their new forms. Each fusion a soft spark, a glow too faint to dazzle. Picture it as a sky at dusk, colors blending into one another, hydrogen's pale shimmer, helium's warm hue, painting a canvas that stretched beyond imagining. It was a time of peace, a pause in the great unfolding. And here's a quiet wonder, these elements weren't strangers to us. The hydrogen flowing through this young universe is the same that runs in your veins. The helium the same that lifts a balloon into the sky. They were born here, in this gentle forge, crafted from the simplest pieces of matter. Scientists call it nucleosynthesis, but it's enough to think of it as a cosmic recipe, 2 parts hydrogen, 1 part helium, a pinch of lithium, stirred in the warmth of creation. It lasted only minutes, yet it left a legacy that spans billions of years. Imagine this scene as a tapestry, threads of matter weaving together in the dimming light. The universe was still too hot for these elements to settle into clouds or stars. They floated free, a mist of possibility carried on the expanding sea. Their birth left echoes, too, patterns in the glow that we can still measure, like ripples frozen in time. It's comforting to know that this quiet crafting shaped the sky we see, that every star burning tonight owes its life to these first, fragile unions. Cosmos was patient, letting its elements drift in harmony, a lullaby of matter taking form. As the minutes passed, the heat continued to fade, the glow growing ever softer. The universe, now rich with these simple elements, stretched wider still, its light thinning into a veil. The time of fusion slowed, then stopped, the forge cooling into stillness. Hydrogen and helium hung in the vastness, a sea of potential waiting for its next chapter. The cosmos didn't hurry, it rested, letting the glow dim further, the light scattering into a haze too faint to pierce. And so, the universe eased into a quieter age, a time when darkness would settle gently over the glow, cloaking the stars yet to be born. The universe drifted into a stillness, its once glowing haze fading into a soft dusk. The light that had bathed its early moments stretched thin, scattering across the vastness like mist dissolving over a quiet lake. This was a time of shadow, a gentle cloak settling over the cosmos. Picture it, a sea of hydrogen and helium, floating free, bathed in a darkness so deep no stars yet pierced it. The universe rested here, in a long, tranquil pause, cooling slowly as it stretched ever wider. This was an age without light, a hush before the dawn of creation's next breath. In this serene expanse, the heat had dwindled to thousands of degrees, warm, but no longer a forge. The elements born earlier lingered, a vast mist of possibility too scattered to glow. Imagine them as whispers of matter, drifting through an endless night, their dance slowed to a gentle sway. Light still moved among them, those ancient photons from the beginning. They were trapped, bouncing softly between particles like echoes in a cavern. The cosmos was opaque, a velvet curtain drawn across its depths, hiding the wonders yet to come. What's enchanting about this time is its quiet mystery. No suns blazed, no galaxies swirled, just an endless sea of calm, stretching in every direction. The universe was cooling, its energy softening, letting the matter settle into a delicate balance. Gravity, ever patient, tugged faintly at the mist, nudging it into subtle ripples, hints of structure too faint to see. These were the seeds of what would be, resting in the dark like bulbs beneath winter soil, waiting for the right moment to stir. It's a soothing thought, a cosmos cradling its future in silence. The science here flows like a lullaby. This age lasted hundreds of thousands of years, a blink in the universe's life, yet a lifetime for its stillness. The temperature fell steadily, from thousands to hundreds of degrees. Slow exhale that let the haze thin. Once so thick it couldn't escape, began to loosen its bonds. Matter and energy, once fused in a glowing embrace, drifted apart, their dance growing gentler with each passing moment. The universe was like a painter pausing before the next stroke, letting the canvas rest in shadow. Feel the texture of this darkness. It wasn't empty or cold, it was full, brimming with the gentle hum of potential. The hydrogen and helium, those firstborn elements, floated in vast clouds, too sparse to ignite, too calm to clash. They stretched with the cosmos, carried by its quiet expansion, a sea without shores. Scientists call this the Dark Ages, but there's no need for gloom. Picture it as a night sky before the stars, a deep, peaceful veil, soft and familiar, wrapping the universe in a tender embrace. It was a time of waiting, not of absence. And here's a quiet marvel. This darkness left echoes we can still touch. As the universe cooled, those ancient photons trapped for so long began to slip free. They stretched with the cosmos, their glow fading into a whisper of warmth we can measure today. This is the cosmic background, a faint hum filling the sky, like the memory of a lullaby sung long ago. It's comforting to know this silent age speaks to us still, its light softened by time, a bridge between then and now. The universe, even in its shadows, was telling its story. Imagine this scene as a dreamscape, all muted tones and gentle shapes. The clouds of matter hung in the void, their edges blurred, their forms too soft to grasp. Gravity worked its slow magic, pulling here, nudging there, weaving patterns that would one day bloom. The cosmos didn't rush, it breathed, letting the darkness cradle its growth. For nearly 400,000 years, it rested in this hush, the light dimming, the matter drifting, a stillness so deep it feels like the universe was sleeping, gathering strength for what lay ahead. As the cooling continued, a shift began to stir. The temperature dropped to a mere glow, a warmth too faint to hold the light captive. The photons, those tireless travelers, broke free at last, streaming through the cosmos in a soft release. The haze cleared, the veil lifted, and the universe became transparent, a sea of matter bathed in quiet shadow. The clouds of hydrogen and helium, once lost in the dark, stood ready now, poised to gather, to ignite. And so, from this long night to the first flickers of light prepared to spark, easing the cosmos into an age where stars would gently wake. The universe, emerging from its long night, began to glow with faint whispers of light. The vast clouds of hydrogen and helium, drifting in the quiet dark, felt a gentle tug, a pull as soft as a breeze stirring leaves. Picture it, a cosmos waking slowly, its shadows parting to reveal the first flickers of radiance. These were the earliest stars, tiny sparks igniting in the stillness, their warmth spreading like candles lit in a vast room. From these humble beginnings, galaxies would bloom, threading the universe with light and wonder. In this tranquil dawn, the matter that had floated free for so long started to gather. Gravity, patient and steady, drew the clouds closer, coaxing them into clumps. Imagine them as mist condensing on a cool morning, each droplet merging until it grew heavy with possibility. Within these pockets, the hydrogen, simple and abundant, pressed together, its heart warming under the weight. Then, in a moment as gentle as a sigh, the first star flared to life, a beacon piercing the endless night. It was a birth without rush, a glow that felt like home. What's beautiful here is the simplicity of it all. These first stars weren't grand or mighty, they were small, fragile even, yet their light was a promise. Made mostly of hydrogen, with traces of helium, they burned in a quiet furnace, fusing their cores into something new. The heat within them, millions of degrees, crafted helium from hydrogen, a slow alchemy that lit the dark. Picture them as fireflies, dotting the void, their soft radiance a lullaby for a universe just waking. They were the pioneers, the first to shine. The science flows like a calm river. This awakening happened hundreds of thousands of years after the universe began. Perhaps 500,000, perhaps 1,000,000. A time when the cosmos had cooled to a mere chill. The clouds collapsed under their own weight, a process as natural as rain falling from a sky. As they shrank, their centers grew dense and hot, sparking fusion, a dance of matter turning to light. These stars, called the first generation, lived fast and bright, but for now, their birth was a gentle unfolding, a spark against the velvet dark. Feel the serenity of this moment. The universe, once a sea of shadow, became a canvas sprinkled with light. Each star was a world unto itself, a glowing ember floating in the vastness. They didn't stand alone for long. Gravity wove them together, pulling stars into clusters, then into the first galaxies. Imagine these as gardens of light, their shapes irregular and soft, like petals scattered across a pond. The cosmos didn't hurry, it let the stars bloom, their glow blending into a tapestry that stretched beyond sight. And here's a soothing marvel. These stars were different from the ones we know. Born of pure hydrogen and helium, they carried no heavier elements, no iron, no gold, just the simplest stuff of creation. Yet they were mighty in their own way, some growing vast before their time was done. When they burned out, they scattered their ashes, new elements forged in their hearts, into the dark, gifts for the stars to come. It's a comforting thought. Every twinkle above us owes its life to these quiet ancestors, their light a bridge across time. Picture this scene as a dream taking shape. The galaxies formed slowly, their arms curling like tendrils of smoke, each one a cradle of stars. The light they cast was faint at first, a shimmer against the endless night, but it grew, spreading warmth through the cold. Scientists say this took millions of years, a heartbeat in the universe's life, yet it feels eternal, a gradual brightening like dawn creeping over hills. The cosmos was alive now, its silence broken by the hum of fusion, a melody too soft to wake the sleeping void. As these stars and galaxies multiplied, the universe began to shift once more. The light they shed chased back the shadows, illuminating the clouds that lingered. The hydrogen and helium, once free and formless, found new purpose, feeding the furnaces of countless stars. The galaxies didn't stand still, they drifted, drawn by gravity's gentle hand, weaving patterns across the vastness. And so, the cosmos eased into a new phase, where the scattered lights would gather further, threading the dark with filaments and walls of glowing matter. A quiet architecture rising from the glow. The universe, now sprinkled with the soft glow of stars, began to weave a larger design. Galaxies, those gentle clusters of light, drifted through the dark, guided by an unseen hand. Picture it, a vast sea of matter and light, slowly threading together like strands of silk in a cosmic loom. Gravity, patient as ever, tugged at the clouds of gas and the newborn stars, shaping them into patterns, delicate filaments, broad walls, and quiet voids. This was the universe finding its form, a tapestry of structure stretching across the endless night. In this serene expanse, the cosmos didn't rush. The galaxies gathered over millions of years, their light blending into rivers of radiance that flowed through the dark. Imagine them as threads of mist, curling and twisting, each one a stream of stars and gas stretching for millions of light years. These filaments glowed faintly, their edges soft, like tendrils of fog drifting over a still lake. Between them lay great sheets, walls of matter so vast they could cradle countless galaxies, their surfaces shimmering with the hum of creation. What's beautiful here is the harmony of it all. The universe wasn't a jumble, it was a web, woven with care. Gravity pulled the hydrogen and helium, those ancient elements, into these shapes, sculpting the chaos into order. Some regions grew dense, birthing clusters of galaxies like pearls on a string, while others stretched thin, leaving empty spaces, voids so deep they swallowed light itself. Picture these voids as quiet hollows, cradles of shadow where the universe rested, balancing the glow of its brighter threads. The science flows like a gentle breeze. This structure took shape as the cosmos expanded, a process spanning hundreds of millions of years. The seeds of it were sown long before, tiny ripples from the universe's birth, stretched and amplified until they guided matter's dance. Stars ignited within the filaments, their light tracing the paths gravity carved. The walls held galaxies too, vast and flat, while the voids grew ever emptier, a contrast that made the web's beauty stand out. It was a slow unfolding, a map drawn in light and shadow. Feel the calm of this vast architecture. The filaments weren't rigid lines, they curved and bent, flowing naturally like rivers finding their way. The walls stood as silent guardians, their surfaces alive with the flicker of stars, yet so broad they seemed still. The voids, dark and deep, offered a hush, a pause between the glowing strands. Together, they formed a network, a cosmic lattice that cradled all that was. It's a soothing image, a universe building itself brick by brick, each piece falling into place with the ease of a sigh. And here's a quiet wonder, this web is still with us. Look up at the sky, and the galaxies you see, faint smudges of light, are part of these same filaments and walls. Scientists map them today, tracing the threads that stretch across billions of light years, a structure so grand it dwarfs imagination. Yet it began so simply, with clouds of gas and the gentle pull of gravity, a dance that turned emptiness into form. The stars within these patterns burned and faded, scattering new elements to seed the next generation, a cycle as peaceful as waves lapping at a shore. Imagine this scene as a painting in motion. The filaments glowed like veins of light, pulsing softly with the life of stars. The walls rose like curtains of mist, their edges blurred, their surfaces alive with distant twinkles. The void sat still, dark pools reflecting the glow around them, a reminder of the universe's vastness. This wasn't a hurried creation, it unfolded over eons, each galaxy finding its place, each thread weaving into the whole. The cosmos was like a gardener, tending its rose, letting the light bloom where it would. As this web grew, the universe continued to stretch, its pattern sharpening with time. The stars within the filaments and walls shone brighter, their light cutting through the dark, while the voids deepened, a silent counterpoint. The cosmos didn't pause, it flowed, carrying its structure forward, a living map of all that had been. And within this glow, echoes lingered, whispers of the universe's birth, stretched thin by its expansion, waiting to be heard. The light of those first moments, once trapped, now hummed faintly across the web, a relic of the calm that came before, ready to tell its tale. The universe, now a vast web of glowing threads and silent voids, carries a whisper from its distant past. This is a faint hum, a glow too soft to see with the eye, yet it fills the sky like a memory woven into the dark. Picture it, a sea of light, born in the earliest moments, stretched thin by the cosmos's endless reach. This is the afterglow of creation, a relic of the time when the universe was young and warm, its echoes drifting through the stars. It's a lullaby from the beginning, soothing and eternal. In this tranquil expanse, the light moves freely now, no longer trapped by the haze of its birth. Imagine it as a breeze, carrying the warmth of a long ago dawn, brushing against the galaxies and voids alike. This glow began when the cosmos was just a few 100,000 years old, when the heat had cooled enough to let light slip free. It streamed outward, a gentle wave of energy, painting the universe with its final farewell to that early glow. Today, it surrounds us, a quiet presence too faint to startle, yet rich with the story of all that came before. What's beautiful here is its timelessness. This light, those ancient photons, has traveled for billions of years, stretched by the universe's expansion until it's no longer a blaze but a whisper. Scientists call it the cosmic microwave background, a name that hints at its softness, like the hum of a distant radio tuned to silence. It's cool now, just a few degrees above the deepest cold, a shadow of the furnace it once was. Picture it as dew settling on the night, a remnant of the heat that birthed the stars, now resting in peace across the sky. The science flows like a calm river. This glow was born when matter and light parted ways, about 380,000 years after the universe began. The hydrogen and helium, once a thick soup, thinned out, letting the photons escape. As the cosmos grew, this light stretched with it, its waves lengthening into a faint murmur we can catch with patient tools. Its uniform, this glow, blanketing the universe in a smooth veil, yet it carries tiny ripples, echoes of the earliest patterns, the seeds of galaxies. It's a map of the past, drawn in light too gentle to disturb. Feel the serenity of this presence. It's everywhere, above you, around you, threading through the dark between the stars. These photons, older than the sun, older than the earth, have seen the universe unfold. They bathed the first clouds of gas, watched the first stars ignite, and now they drift through the web of filaments and walls, a constant companion to the cosmos. Imagine them as fireflies from a forgotten time, their glow dimmed but never lost, a soft blanket wrapping the universe in its own history. And here's a quiet marvel. We can hear this whisper today. With dishes pointed at the sky, we catch its hum, a static too faint for ears, but alive with meaning. It's the oldest light we know, a snapshot of the universe as a toddler, still smooth and warm. Those tiny ripples within it, so small they're like breaths on glass, tell us how matter clumped, how galaxies found their place. It's comforting to think this glow connects us to the beginning, a thread of light tying now to then, a reminder that the cosmos remembers its youth. Picture this scene as a painting, all muted tones and gentle sweeps. The universe glows with this relic light, a haze too soft to dazzle, yet it outlines every star, every void. It's a background to the web, a canvas beneath the threads of galaxies. Its uniformity a lullaby for the vastness. Scientists measure it, map it, finding in its patterns the shape of the cosmos itself, flat, endless, expanding still. It's a thought to drift with, letting the hum settle over you like a warm night. A bridge between the universe's first sigh and the sky you see. As this glow continues its journey, it weaves into the fabric of all that is. The stars shine against it, the galaxies drift within it, and the universe expands, carrying this light further still. It's a constant, a gentle pulse from the past, humming through the present with no end in sight. And so, birds, the story of the cosmos flows on, from this ancient echo to the wonders it holds today, easing into a tale of all that has been and all that might yet be, a calm unfolding beneath the stars. Every night, astronomers peer into the vast expanse of the cosmos, their telescopes trained on distant stars in a relentless quest for habitable worlds and faint whispers of alien radio signals. So far, the universe has remained stubbornly silent. No definitive signs of life have emerged from the dark void. But does this mean their efforts are futile? Are we truly alone in this immense tapestry of space? This question carries profound weight, as its answer shapes our understanding of humanity's place in the grand scheme of the universe. One compelling idea, known as the rare Earth hypothesis, suggests that perhaps we shouldn't expect to find life scattered across the stars. According to this theory, Earth might be an extraordinary anomaly, a singular cradle of life in an otherwise barren cosmos. But is this hypothesis sound? To explore this, let's start with the big picture. Zoom in on the hypothesis itself, and then examine recent discoveries to see if they align with or challenge this perspective. Here's the roadmap we'll follow. We'll dive into a topic that's fresh for discussion, weaving together a variety of concepts that promise to captivate your curiosity. You've likely encountered the notion of a star's habitable zone, that sweet spot around a star where conditions are just right for liquid water to exist, neither too scorching nor too frigid, often dubbed the Goldilocks zone. It's the region where exoplanets might have the potential to support life as we know it. But did you know that galaxies themselves have habitable zones? Not every galaxy is equally hospitable to life. Stars farther from a galaxy's core tend to have lower metallicity, a term astronomers use to describe the abundance of elements heavier than helium. These heavier elements, essential building blocks for planets and life, are forged in the fiery hearts of massive stars and scattered into space by supernova explosions. Such stellar furnaces are far more common near the bustling galactic center, where raw materials are plentiful. Consequently, stars on a galaxy's outskirts often lack the critical ingredients needed to form rocky planets capable of sustaining life. Closer to the galactic core, however, a different peril emerges. Most spiral galaxies, like our Milky Way, harbor supermassive black holes at their centers. These cosmic titans can unleash torrents of X-rays and gamma rays, bathing nearby regions in lethal radiation. Any exoplanet orbiting too close would be relentlessly bombarded, rendering it uninhabitable. Life, as we understand it, could never take root under such harsh conditions. Then there are the galaxies' spiral arms, stunning features of dense star formation that sweep outward from the core. While beautiful, these regions are treacherous for life. Stars within the arms frequently pass near one another, their gravitational interactions disrupting the delicate orbits of orbiting planets. Imagine Earth suddenly veering onto Mercury's sun-scorched path. Any budding life would be snuffed out in an instant. Additionally, the spiral arms are hotspots for supernovae, which erupt with deadly radiation that sterilizes anything in their vicinity. So, the Gulick habitable zone strikes a delicate balance. It's a region close enough to the core to benefit from sufficient metallicity, yet distant enough from the center and spiral arms to avoid catastrophic gravitational tugs and radiation overloads. Our understanding of this zone is still evolving, and we're only beginning to map out which parts of the Milky Way, or any galaxy, might be suitable for life. In the Milky Way, these constraints likely render the vast majority of stars unfit to host life-bearing planets. Even among the remaining candidates, a star must be of the right type and possess a planetary system structured in a way that nurtures life. Once, we assumed every star had a habitable zone where liquid water could theoretically exist. But this view oversimplifies the complexities of stellar and planetary dynamics. Take low-mass stars, for instance. These dim, cool stars emit far less visible and infrared light than their brighter counterparts on the main sequence, like our Sun. Yet they can unleash intense bursts of X-rays and gamma rays. While their habitable zones might technically allow for liquid water, the radiation levels could shred complex molecules, obliterating any chance of life taking hold. Our Sun, by contrast, is remarkably stable, with its luminosity fluctuating by less than 0.1%. Other stars, however, can vary wildly, some by as much as 500%. Such drastic swings shift the boundaries of their habitable zones, plunging planets in and out of life-friendly conditions. A world might bask in habitability one moment, only to freeze or boil the next, erasing any prospects for sustained life. Even if we pinpoint a star with the right characteristics, the presence of a life-friendly planet is far from guaranteed. The arrangement of a planetary system plays a pivotal role. In our solar system, rocky planets like Earth huddle close to the Sun, while gas giants like Jupiter orbit farther out, a configuration that's surprisingly rare. Most exoplanetary systems discovered so far feature either all rocky worlds or gas giants parked perilously close to their stars, dubbed hot Jupiters. Our system's unique layout, with its blend of inner rocky planets and outer giants, may have been a key factor in life's emergence here. The number and arrangement of planets in a system also matter. Systems with just one or two exoplanets often exhibit highly elliptical orbits, causing planets to swing in and out of the habitable zone over the course of their year. Yet another strike against life. In contrast, systems with multiple larger planets can develop orbital resonances, where gravitational interactions stabilize orbits into near-circular paths. This stability allows a planet to linger in the habitable zone consistently, boosting its odds of supporting life. Orbital resonance is a complex dance of gravitational harmony. It keeps planets in their proper places, preventing chaotic deviations. If Earth began drifting too close to the Sun, these resonances would tug it back into line, and vice versa. This equilibrium has been vital to our planet's long-term habitability, but even with stable orbits, the right mix of rocky and gaseous planets, and a star of the ideal type, the chances of finding life remain slim. Consider Jupiter's role in Earth's story. Models of the early solar system suggest this gas giant was instrumental in life's development. Its gravitational influence shepherds the asteroid belt, locking countless rocky fragments between itself and Mars. Without Jupiter, Earth would face a relentless barrage of impacts, making it nearly impossible for life to gain a foothold, or even begin. In the solar system's infancy, Jupiter briefly spiraled inward, threatening to obliterate the inner planets. Fortunately, its resonance with Saturn intervened. Saturn's gravitational pull yanked Jupiter back, averting disaster and preserving Earth and Mars. This intricate interplay underscores the notion that a specific planetary configuration, complete with a Jupiter-like guardian, may be a prerequisite for life as we know it. Yet even this isn't the full picture. A planet's size, composition, and geological activity are equally critical. Too small, and a planet struggles to retain an atmosphere or liquid water. Mars is a stark example, its thin air and dry surface a testament to its diminutive stature. Too large and excessive gravity could trap a crushing atmosphere, stifling life. Atmospheric composition also matters. Venus, despite orbiting within the Sun's habitable zone, suffocates under a thick blanket of carbon dioxide, its surface hotter than a furnace. Plate tectonics, Earth's restless shifting of continental plates, further complicates the equation. This geological process, driven by the churning of molten rock in the planet's core, shapes mountains, triggers volcanic eruptions, and carves oceanic trenches. Many scientists believe life first sparked near hydrothermal vents, fissures on the seafloor fueled by tectonic activity. Without tectonics, those primordial cradles might never have formed. Tectonics also sustains complex life. The movement of plates recycles nutrients and regulates the carbon cycle, stabilizing Earth's climate over eons. This dynamism stems from the planet's molten, iron-rich core, which generates a magnetic field. That field shields Earth from the solar wind, a stream of charged particles that would otherwise strip away the atmosphere. Mars, lacking a robust magnetic field, lost much of its air to this cosmic erosion. Earth's tectonic vigor owes a debt to an unlikely ally, the Moon. Our lunar companion is unusually large, weighing in at 27% of Earth's mass, a rarity among planetary moons. Its gravitational pull stirs Earth's oceans, creating tides that heat the planet's mantle through friction. Without this lunar influence, tectonic activity might stall, undermining life's prospects. The Moon also steadies Earth's axial tilt, the gentle 23-degree lean that gives us seasons. Without this stabilization, wild wobbles could plunge the planet into climatic chaos. Imagine then an exoplanet ticking all these boxes, positioned in a galaxy's habitable zone, orbiting a stable star nestled in a balanced planetary system, with the right size, composition, tectonics, and a massive moon. Would life thrive there? Quite possibly. Scientists are probing Mars for clues, seeking traces of ancient life from a time when it boasted oceans, tectonics, and a thicker atmosphere. If evidence emerges, it could bolster the case for life on distant worlds, albeit simple life, akin to bacteria. Complex life, like multicellular organisms or intelligent beings, demands even rarer conditions. Earth hosted life for at least 3.5 billion years before anything sophisticated appeared. For most of that time, only single-celled organisms prevailed. Then, around 540 million years ago, the Cambrian explosion ignited a surge of diversity. Following a glacial epoch, melting ice flooded the oceans with nutrients, sparking an algal bloom that oxygenated the atmosphere. Tectonics sculpted the mountains that supplied those nutrients, making this leap possible. Within millions of years, life evolved from simple, sponge-like forms to crustaceans, squid, vertebrates, and starfish. Yet even these Cambrian marvels were far from intelligent. The journey from single cells to complex ecosystems hinged on flukes, random cellular collaborations that took eons to coalesce. Multicellularity itself may be a cosmic stroke of luck, its odds of replication vanishingly small. To summarize, a planet needs a staggering confluence of factors to harbor life: a galactic sweet spot, a suitable star, stable orbits, the right planetary neighbors, optimal size and composition, active tectonics, a hefty moon, and a natural upheaval to spark complexity. Earth's uniqueness seems almost miraculous, suggesting duplicates are exceedingly rare. But recent findings complicate this narrative. Moons like Europa, Jupiter, and Enceladus, Saturn, harbor subsurface oceans and possible hydrothermal vents, potential havens for life. If even simple organisms lurk there, the rare Earth hypothesis falters, replaced by a broader vision of habitability that includes icy satellites. With gas giants common in the galaxy, and many likely hosting similar moons, the tally of life-friendly worlds could soar. So, are we alone? The search continues, each discovery peeling back the universe's secrets. Earth may be rare, but life's tenacity might yet surprise us. The search for a twin to Earth might never bear fruit. Yet, it seems increasingly plausible that somewhere out in the vast expanse of space we could stumble upon worlds, and perhaps even forms of life, far stranger and more fantastical than anything we've encountered on our own planet. So, what do you think? Are we truly alone in the universe? Astronomers have already cataloged thousands of confirmed exoplanets within our Milky Way galaxy alone. By their estimates, though, the total number of such worlds in our galactic neighborhood could exceed 50 billion, and that's just one galaxy. If we extend our imagination to include the countless other galaxies scattered across the cosmos, the numbers become almost unfathomable. With such staggering odds, it's hard to swallow the idea that intelligent life emerged only on this one tiny speck of a planet we call home. But then a perfectly reasonable counter-argument arises. If intelligent life is so common, why haven't we heard from any extraterrestrial civilizations? Not long ago, I had the chance to visit a modest little aquarium. It wasn't a grand facility by any means, just a handful of tanks, but it captivated me nonetheless. I found myself lingering by each exhibit, peering into the watery worlds housed within. I watched the fish glide through the water with an effortless grace, some resting in the shade of artificial tropical plants. A few darted away as if shy of my gaze, while others seemed engrossed in their own affairs. And then there were those who stared back at me, their curiosity as palpable as my own. What struck me most was their lack of fear. They seemed at ease, secure in their sheltered environment. It felt in a way like they were at home. But as I stood there, I couldn't shake a nagging thought. Aquariums, like oceanariums, are artificial constructs. For the aquatic creatures of our world, these places offer safety and a semblance of freedom. Yet, from another perspective, they represent a human intrusion into the natural order. We've plucked these animals from their wild habitats, deeming them beautiful or rare, and in doing so, we've arguably diminished their quality of life. They're confined. their existence shaped by our whims. This duality makes aquariums, and by extension zoos, deeply ambiguous spaces. They're showcases of nature's wonders, yet also reminders of our tendency to control and contain. I wonder where the astronomer John Ball got the spark for his idea back in the 1970s. Was he standing by an aquarium tank, lost in thought, or did it strike him elsewhere? Regardless, he proposed a striking notion. What if humanity itself is living in a zoo, blissfully unaware of our captivity? The concept caught on, gaining traction first among scientists and later seeping into the realm of science fiction. Initially dubbed the zoo hypothesis, this idea posits that we're part of a cosmic enclosure. However, since it lacks testable evidence, some prefer to call it the zoo scenario. It's a speculative answer to a question famously posed by the Italian physicist Enrico Fermi in 1950. Where is everybody? Fermi's paradox highlights a glaring contradiction in our understanding of the universe. If extraterrestrial life, especially intelligent life, is not just possible but probable, why haven't we seen any sign of it? Is there a biological or sociological reason for this silence? The zoo scenario offers one explanation, and by now you've likely pieced it together. In essence, the zoo scenario suggests that the reason we haven't detected alien life is that Earth is a designated preserve, a galactic wildlife sanctuary of sorts. Advanced civilizations may indeed exist, perhaps in droves, but they've chosen to leave us undisturbed. Picture humanity tucked away in one of the Milky Way's spiral arms, isolated from the bustling hubs of cosmic society. It's not unlike how we set aside pristine tracts of land on Earth for animals to thrive, untouched by our sprawling cities and highways. The zoo scenario draws heavily on humanity's own history. We've dissected nature, harnessing it for our bridges, skyscrapers, farmland, and sun-drenched vacation resorts. Yet we've also carved out pockets, national parks, reserves, zoos, and oceanariums, where wildlife can persist under our watchful eyes. If we use these spaces to study and admire Earth's creatures, isn't it conceivable that supremely advanced civilizations might do the same on a grander scale? In this view, Earth isn't just a planet, it's a living exhibit. But unlike our zoos where we observe lions or elephants, these extraterrestrial overseers are studying us. The prime directive variation of the zoo scenario takes it a step further. It suggests that intelligent civilizations have collectively agreed to leave habitable planets alone, having reached a state of equilibrium, sometimes called a steady state. In this phase, they no longer feel the urge to expand aggressively or colonize new worlds. Science fiction paints vivid pictures of such a future. Civilizations dwelling in massive, self-sustaining arcs, no longer tethered to planetary systems or even orbiting conventional stars. Perhaps they harness the rare but colossal energy of hypergiant stars to power their societies. In this era, information becomes the ultimate currency. Earth, then, might be more valuable to them as a pristine data source than as a territory to conquer. When we visit zoos, we marvel at how a tiger paces its enclosure or a monkey swings between branches. Similarly, these advanced beings might observe Earth over eons, tracking the journey of life from fragile single-celled organisms to rocket-building engineers. So how could we coax these cosmic zookeepers into revealing themselves? Imagine strolling through a zoo when a zebra suddenly locks eyes with you, stomps its hoof, and taps out a sequence of prime numbers. That would shatter the boundary between observer and observed, forcing us to respond. As Mehdi Douglas Vakucha, a thinker on this subject, once put it, we could do the same, beam powerful, deliberate, information-rich radio signals toward nearby stars. It's a bold move, a cosmic knock on the door. Among the zoo scenario's many offshoots, one testable idea stands out: the planetarium hypothesis. This theory probes just how far an alien civilization might go to keep us in the dark. A planetarium, after all, is a theater of illusions. It projects dazzling images of stars, constellations, and planets onto a dome, creating the sensation that those distant realms are within reach. But it's a facade, a carefully crafted simulation. The planetarium hypothesis suggests that our entire universe might be a projection, designed to convince us that space is devoid of intelligent life. Consider the Voyager probes. Voyager 1 and 2 have ventured roughly 150 and 124 astronomical units from Earth, respectively. At such distances, any simulation would start to show cracks, imperfections in the fabric of our perceived reality. Testing this could yield clues that things aren't as they seem. Some latch onto the planetarium idea with fervor, claiming space itself is a hoax, a dome, or a projection. But this theory raises more questions than it answers. For one, it ascribes human-like motives to aliens. If a civilization pursues technological advancement, it likely values curiosity and scientific inquiry, traits that could drive them to study Earth. Yet why would every alien society agree to this non-interference pact? If the galaxy teems with diverse cultures, wouldn't at least one rogue faction break ranks for its own gain? Perhaps there are only a handful of civilizations, or even just one. Still, the scenario assumes universal compliance, with all aliens shielding us from contact or invasion. Why would they bother? What makes humanity so special? Maybe we're overestimating our significance. Perhaps these beings aren't our intellectual kin, but entities so advanced that they can observe and analyze us without ever needing to say hello. Picture a single, omnipotent civilization imposing this rule on all others. If power is concentrated in one species' hands, dissent becomes irrelevant. Lesser societies would have no choice but to fall in line. This, however, implies a level of interstellar coordination that's hard to fathom. Mathematical models of galaxy-spanning communication highlight the challenge. Light speed limitations mean civilizations would need to emerge near simultaneously, persist for millions of years, and cluster within the galaxy's habitable zone to maintain reliable contact. These logistical hurdles leave scientists divided on whether a dominant civilization could enforce such a universal code. The zoo scenario, then, hinges on a delicate balance of conditions, a sobering thought. It suggests that even if alien life exists, we might never know it because they've chosen to stay hidden. But if the zoo hypothesis feels far-fetched, consider an even wilder alternative: the galactic quarantine. Here, aliens recognize that contact would shatter our cultural foundations. Instead, they bide their time, subtly preparing us for an eventual meeting, patiently, methodically, without haste. I adore animals and cherish their presence, yet I'm acutely aware that keeping them denies them agency. If the zoo scenario holds truth, it's an unsettling injustice. A network of civilizations deciding our reality for us, concealing the universe's true nature, that feels fundamentally wrong. I'd argue the cosmos doesn't operate that way. Perhaps we're simply waiting for an old adage to prove itself: all that is hidden will be revealed. Since humans first emerged, we've climbed from cave dwellers to moonwalkers, reshaping our world to suit our needs. More crucially, we've pursued knowledge relentlessly. But is there an endgame? Will we ever reach a point where there's nothing left to discover? To survive the challenges ahead, humanity must ascend to new heights of development. In 1964, Soviet astrophysicist Nikolai Kardashev devised a scale to measure a civilization's technological prowess based on energy mastery. You might know it as the Kardashev scale. It outlines 3 tiers. Type 1 harnesses all energy on its planet, a planetary civilization. Type 2 taps its stars' full output, a stellar civilization. Type 3 commands an entire galaxy's resources, a galactic civilization. Kardashev stopped at Type 3, deeming it the pinnacle. Later thinkers, like sci-fi author Helga Kautz, pushed further, envisioning a Type 4 that exploits a galactic supercluster's energy. Today, we're not even a Type 1, more like a Type 0.7, inching toward planetary mastery. The scale underscores our potential and our limits. Could we one day join the ranks of those watching us from afar? Or are we destined to remain exhibits, peering out from our cosmic enclosure, wondering who or what lies beyond? Imagine a civilization so advanced that it harnesses the energy of the entire universe. This is what we might call a Type 5 civilization on the Kardashev scale, an entity capable of tapping into the boundless power that fuels stars, galaxies, and the very fabric of cosmic existence. Within this grand framework, there exists a subtype, a Type VB civilization, which possesses the remarkable ability to tweak certain fundamental aspects of universal physics. It's a mind-boggling concept, altering the rules that govern reality itself. And then, pushing the boundaries even further, we arrive at a Type 6 civilization. This pinnacle of development can not only wield the energy of its own universe, but also reach beyond, drawing power from other universes within a sprawling multiverse. These extraordinary entities are often referred to as non-Kardashev civilizations, transcending the traditional scale devised by Nikolai Kardashev to measure technological progress based on energy consumption. It's evident that humanity is nowhere near achieving Type 6 status. We're still taking our first tentative steps on this cosmic journey, barely scratching the surface of what's possible. Yet, it's not entirely fair to dismiss the idea as unattainable. If we continue to evolve generation after generation, pushing the limits of science, technology, and imagination, who's to say we can't someday reach such heights? Every monumental achievement begins with a spark of thought, a vision of what could be. To predict the future, we must first dare to create it. So, let's embark on that creative exercise and explore what a Type 6 civilization might look like. Picture a time when humanity has ascended to godlike status. At the level of a Type 6 civilization, people would wield absolute dominion over their universe, shaping it according to their desires. By then, we'd have unraveled one of the greatest mysteries. Are we alone in a single universe, or are we part of an infinite multiverse? If the latter proves true, we'd traverse this vast network of realities with ease. The key to such interstellar and interdimensional travel? Wormholes, tunnels through the fabric of space-time that collapse vast distances into mere steps. Today, wormholes remain a tantalizing theoretical concept, born from the equations of general relativity. But for a Type 6 civilization, they'd be as commonplace as bridges are to us now. Imagine a journey that would take thousands of years in conventional spaceflight reduced to a matter of minutes. The energy required to sustain such feats would be incomprehensible to our current understanding, drawn perhaps from sources we can scarcely fathom, like the elusive dark matter that permeates the cosmos. This mysterious substance, invisible yet gravitationally potent, could become the ultimate fuel for a civilization that has mastered every nook and cranny of scientific knowledge. At this stage, science wouldn't just be a tool, it would be an art form, perfected to its utmost potential. Every field, from quantum mechanics to biology, would reach its zenith, granting us an unparalleled understanding of existence. This mastery would redefine what it means to be human. Disease and death, relics of a primitive past. Nanotechnology would repair our bodies at the cellular level, reversing aging, regenerating organs, and healing any injury imaginable. We'd transcend the need for medicine as we know it, our physical forms becoming infinitely adaptable. Transportation, too, would become obsolete. Why bother with vehicles when teleportation is an option? The laws of physics, once rigid and unyielding, would bend to our will, serving as the building blocks of a blissful, effortless existence. Research fields like theoretical physics might even fade away, not because they failed, but because there'd be nothing left to discover. We'd have mapped the entirety of natural law, turning it into a playground for our ambitions. Our curiosity wouldn't stop at physics. A Type 6 civilization would catalog every life form in the universe, from the simplest microbes to the most complex sentient beings. Better yet, we'd learn to create life from scratch, tailoring it to our specifications. Natural disasters, earthquakes, hurricanes, volcanic eruptions would no longer pose a threat. We'd control the elements, adjusting climates to suit our preferences or neutralizing storms before they form. An asteroid hurtling toward Earth? A minor inconvenience. We'd redirect its path or dismantle it entirely with a flick of our technological wrist. But perhaps the most profound leap would be our transcendence beyond the physical. A Type 6 civilization might abandon corporeal existence altogether, uploading consciousness into a non-physical dimension of our own design. Freed from the frailties of flesh, aging, sickness, mortality, we'd exist as pure intellect, an eternal collective unbound by time or space. In this cloud of consciousness, resources would be limitless. Energy, matter, and information would flow endlessly, far exceeding anything we could ever consume. Each individual could claim their own planet if they wished, sculpting it into a personal paradise. The sheer abundance would defy description, every need met, every dream realized. It's hard to fully capture the scope of what such a civilization could achieve. What else might we envision? Perhaps the ability to rewrite history, simulate alternate realities, or commune with beings from other dimensions. The possibilities stretch beyond the horizon of our current imagination. Doesn't it sound like a delectable future? Before we get too carried away, though, let's ground ourselves. There's another type of civilization I nearly overlooked. Type 0. That's us. Humanity as it stands today, fumbling along at the base of the Kardashev scale. Experts estimate it'll take at least a century to claw our way up to Type 1, where we'd harness the full energy output of our planet. It's a daunting endeavor, riddled with obstacles that could halt our progress, or worse, erase it entirely. One chilling explanation for our slow ascent is the Great Filter, a hypothesis tied to the Fermi paradox. Economist Robin Hanson proposed this idea to address why we haven't encountered other advanced civilizations. The Great Filter suggests there's a barrier, some insurmountable challenge, that prevents most species from reaching a detectable level of advancement. In the context of the Kardashev scale, it's the hurdle keeping us from climbing higher. Physicist David Brin, a NASA consultant, finds this scenario plausible. He argues that even one civilization embracing this ruthless mindset could enforce a galaxy-wide hush. The moment a fledgling species starts chirping, it's silenced, vaporized by a watchful elder race. Our own signals, though, might not be loud enough to doom us. Everyday transmissions weaken as they spread, dissolving into cosmic static long before they reach distant ears. But that raises a wrinkle. Can any civilization stay perfectly quiet forever? A single slip, a rogue broadcast, a careless probe, could unravel the masquerade. And if someone's hunting for signs of life, Earth's bustling biosphere might already be a glaring beacon. The night deepens as you quicken your pace, the stranger's silhouette fading into the fog behind you. Back on Earth, the unknown can be navigated. If danger strikes, there's a chance for rescue. Friends, passers-by, the wail of a siren. In space, there's no such comfort. No cavalry rides to the rescue across light years. If an alien armada descended, we'd be alone, staring into the abyss with no one to hear our screams. But what if the dark forest isn't the whole story? What if its shadows hide not just hunters but alliances? Picture a coalition of species pooling their knowledge, trading resources, and leaping across the stars together. Cooperation has fueled humanity's rise. Cities, nations, fragile truces, despite our penchant for war. Couldn't extraterrestrials see the same value? Liu Cixin counters this with his chain of suspicion. Even if two civilizations could talk, the gulf between them, distance, culture, time, breeds doubt. A younger race might seem harmless today, but technology doesn't creep. It surges. A sapling civilization could bloom into a juggernaut in mere centuries, turning yesterday's friend into tomorrow's foe. Stephen Hawking agreed, warning against reckless cosmic chatter. He likened it to indigenous tribes signaling conquistadors. History shows how that ends. Dozens of scientists have echoed him, some even petitioning to halt active SETI, search for extraterrestrial intelligence efforts. Who gets to roll those dice for humanity? A lone researcher? A government? The question hangs unresolved, a moral quandary as vast as the universe itself. Step back to that moonlit street. The fear you feel isn't alien, it's human. We've built the dark forest theory from our own instincts, our wars, our betrayals, our moments of grace. It's a mirror reflecting how we treat each other, then projected onto the stars. Maybe we're wrong to paint extraterrestrials as merciless killers. If they evolved under conditions like ours, carbon-based, water-reliant, they might share our flaws and our virtues. History brims with conquerors crushing the weak, but also with alliances lifting the fallen. Could an alien mind be kinder, wiser, or darker still? The fog thickens as you near home, the stranger lost to the night. You lock the door, safe for now, but the questions linger. Out there, beyond the atmosphere, the universe watches. Is it a forest of hunters, each trigger primed, or a tapestry of voices waiting for the right moment to sing? The Fermi paradox persists, a riddle wrapped in silence. Maybe they're hiding, maybe they're gone, or maybe, just maybe, they're closer than we think, listening as we stumble through the dark. The wind howls across a prehistoric plain, stirring the dust of a world still young. Beneath a sky streaked with the fiery hues of dawn, two groups of humans stand on the cusp of destiny. One, a band of dark-skinned hunters with striking blue eyes, grips spears carved from bone. their gazes scanning the horizon for game. The other, a tribe of light-skinned newcomers, tills the soil with crude tools, their brown eyes fixed on the tender shoots breaking through the earth. This is no mere meeting of strangers, it's a collision of fates, a quiet war waged not with weapons, but with the slow, relentless march of genes. Over millennia, the newcomers will triumph, their traits weaving into the fabric of Europe's future. This is the story of human evolution, a tale as old as life itself, yet as fresh as the questions it leaves unanswered. Picture Europe thousands of years ago, a sprawling canvas of forests, rivers, and rolling hills. The native hunters, descendants of Africa's primal wanderers, roamed these lands with a grace honed by survival. Their dark skins soaked up the sun's rays, a shield against the ultraviolet blaze of their ancestral homeland. Their blue eyes, a genetic rarity, gleamed like sapphires against the rugged landscape, a fleeting beauty destined to fade. Then came the newcomers, migrants from the sun-scorched plains of the Near East, their lighter skin and brown eyes heralding a new way of life. They brought with them the secrets of the soil, agriculture and animal husbandry, upending the ancient rhythm of the hunt. In this shift, the seeds of dominance were sown. Why did these newcomers prevail? The answer lies in the alchemy of adaptation. Farming demanded a different diet. Grains, milk, and vegetables replaced the protein-rich feasts of meat that sustained the hunters. Vitamin D, once plentiful in the flesh of prey, now trickled in smaller doses from sunlight and dairy. Dark skin, once an asset, became a liability in the cloudy north, hindering the body's ability to synthesize this vital nutrient. Light skin, by contrast, drank in the scarce rays, offering a subtle edge in survival. The brown-eyed farmers carried genes better suited to this new world, and nature, ever the impartial judge, favored them in her grand ballet of selection. Charles Darwin called it natural selection, a slow, elegant dance where the environment partners with life, choosing those best equipped to thrive. It's not a sprint, but a marathon spanning generations, a process that reshapes species over thousands or even millions of years. The hunters didn't vanish overnight. Their blue eyes lingered, a recessive whisper in the gene pool. But the tide of brown-eyed dominance swelled with each passing century. Eastern influences trickled in too, threads of DNA from tribes ancestral to modern Siberians and Native Americans, blending into the European crucible. What emerged was a new archetype, light-skinned, brown-eyed, a testament to adaptability's quiet power. This wasn't destiny carved in stone, it was probability sculpted by circumstance. How long did it take for these traits to reign supreme? 1,000 years? 10,000? The fossil record offers no precise clock, only snapshots of a gradual shift. Yet the outcome is undeniable. The hunters, once lords of the wild, yielded to the farmers, their legacy diluted in the bloodlines of a continent transformed. Evolution, as Darwin saw it, is less about glory than survival. Those who fit the mold pass their essence forward, while the rest fade into the shadows of time. Consider the journey of another creature, Hyracotherium, a dog-sized denizen of ancient forests. 55 million years ago, it trotted on four-toed forelimbs and three-toed hind limbs, a delicate frame suited to a leafy world. Over eons, nature whittled away at its form. Toes merged, legs lengthened, and the middle digit stretched into a hoof. By the time it galloped across plains as the modern horse, towering and swift, countless generations had danced with extinction and triumphed. Such transformations demand patience, Millions of years of trial and error, each step a gamble against oblivion. But evolution isn't always a plodding giant. Sometimes it leaps. Biologists Peter and Rosemary Grant, peering through the lens of Princeton's labs, watched Darwin's finches on the Galapagos Islands morph in real time. A drought struck, seeds grew scarce, and birds with stubby beaks struggled to crack the tough husks. Their long-beaked kin, however, thrived, prying open nature's larder with ease. Within a single generation, beak size shifted. A microevolution sparked by climate's cruel hand. Survival hinged on the tools at wing. Short beaks spelled hunger, long beaks offered hope. Yet this wasn't permanent. A shift in diet, say softer fruits, could shrink those beaks again, proving evolution's flexibility, its readiness to pivot with the winds of change. David Lottie and Paul Ewald, evolutionary scholars, argue there's no rigid script. The tempo of change, fast or slow, fleeting or lasting, depends on nature's hostile forces: predators, parasites, scorching heat, or biting frost. Darwin himself noted these pressures, the gauntlets that test a species' mettle. For Europe's farmers, the hostile force was a subtler foe, a sun-starved climate demanding new adaptations. Their gene pool brimmed with variety, a buffet of traits for nature to sample. The hunter's darker skin and blue eyes, once assets, couldn't keep pace with a world remade by plow and pasture. The farmer's genes, leaner and more attuned, claimed victory in this silent struggle. Humans, though, are more than mere pawns of biology. Social selection, Lottie and Ewald suggest, sculpted our minds as much as our bodies. The brain's complexity, our knack for cooperation, conflict, and cunning, grew from the push and pull of tribal life. Did the hunters and farmers clash in bloody skirmishes, spears meeting sickles under a cold moon? Or did they trade, marry, and mingle, their bloodlines entwining in peace? The truth lies buried, lost to time's erosion. What we know is the result: a dominant palette of features, light skin, brown eyes, etched across a continent. In Scandinavia, the palette shifts again: pale skin and fair hair, a response to even dimmer skies, a lifeline to vitamin D in a land of long winters. Today, the climate churns faster than ever. Storms rage, ice melts, summers blister. Could this spark fresh changes in humanity's form? A slight tweak in skin tone, a nudge in stature. The where, when, and how remain elusive, veiled by evolution's unpredictability. It's a ceaseless engine grinding forward as conditions shift. Some groups will edge ahead, their offspring better tuned to the new normal, while others falter. That's natural selection's essence, an endless adaptation to an ever-spinning world. Wild-eyed theorists dream bigger. Picture humans with bulbous heads and spindly limbs, like the gray-skinned aliens of sci-fi lore. Or imagine us evolving shark-like flexibility, our bones softening into cartilage for resilience and childbirth. Tempting as these visions are, they lean more on gene editing's promise than evolution's slow grind. Natural selection doesn't chase whimsy, it hones what works, pruning the rest. Our future likely holds subtler shifts, molded by viruses, warming skies, and the societies we build. Prediction is a fool's game. Evolution thrives in the cracks of the unexpected. Zoom out far beyond humanity's flicker to Earth's deep past. 700 million years ago, the planet shivered under a frozen shroud. The snowball Earth hypothesis paints a world encased in ice, from pole to equator, not once but twice. The Sturtian glaciation gripped the globe around 710 million years ago. The Marinoan followed at 635 million, both scars of a cryogenian chill. Geologists unearthed their echoes in Namibia's limestone-streaked cliffs, rock-born in warm seas now sandwiched by glacial scars. From space, Earth gleamed white, a marble of frost and silence. Imagine it. No liquid water, just a crust of ice miles thick, dusted with frost from a frigid sky. Temperatures plunged to -50 Celsius, winds howled across barren lows, and the water cycle stalled. Beneath the ice, a dark ocean churned, stirred by tides and geothermal whispers from the deep. Life clung on, huddled near volcanic vents, a faint pulse in a frozen abyss. What triggered this icy doom? The breakup of Rodinia, a supercontinent fracturing over 200 million years, set the stage. As land split, rains intensified, weathering rock and siphoning carbon dioxide from the air, a cooling spiral. Then, in what's now Arctic Canada, volcanoes roared between 717 and 719 million years ago, spewing sulfur aerosols that bounce sunlight back to space. Ice's high albedo, reflecting up to 80% of solar rays, locked the cold in place, a feedback loop of frost. Yet from this desolation sprang life's next act. The Cambrian explosion, igniting 501 million years ago, saw complex creatures diversify. Trilobites, worms, the ancestors of us all. The snowball's thaw, geologists argue, primed the pump, stirring nutrients into a reborn sea. Earth's tale is one of upheaval and renewal, a saga of ice and fire that shaped the dance of evolution still unfolding. Humanity, a latecomer, inherits this legacy, our genes a mosaic of victories, our future a question mark etched in the stars. Imagine a planet adrift in the void, its surface a glistening shroud of ice that stretches from pole to pole. No waves crash against rocky shores, no rivers carve through verdant valleys, only a silent, endless expanse of frost glitters beneath a weak, distant sun. This is Earth, 700 million years ago, locked in the grip of a deep freeze so profound it defies comprehension. The air bites with a chill that sinks to -50 Celsius, and the sky, a pale vault of unrelenting gray, offers no warmth. Beneath the ice, a dark ocean stirs, its currents driven by the faint heartbeat of volcanic vents far below. This is the snowball Earth, a world-turned tomb, yet a cradle for life's next chapter. Long before this icy epoch, the supercontinent Rodinia reigned supreme, a vast mosaic of land masses stitched together across the planet's face. But nothing lasts forever. Around 750 million years ago, Rodinia began to fracture, its seams splitting under tectonic strain. As the continents drifted apart, they unleashed a fury of volcanic eruptions, spewing ash and sulfur into the heavens. These fiery outbursts, stretching across what's now Arctic Canada, lasted millennia, their plumes rising high into the stratosphere. There, sulfur aerosols lingered, a shimmering veil that bounced sunlight back into space, chilling the planet degree by degree. The stage was set for the first snowball Earth, the Sturtian glaciation, a 58 million year odyssey into frost. What transformed Earth into this frozen sphere? The breakup of Rodinia didn't act alone. As rains lashed the newly sundered lands, they eroded rock, leaching carbon dioxide from the atmosphere, a process called weathering that sapped the greenhouse gas keeping the planet warm. Couple that with a sun 6% dimmer than today, and ice began to creep. It started at the poles, then marched equatorward, its reflective surface, its albedo, amplifying the cold. Ice reflects up to 80% of sunlight, unlike the dark oceans that drink it in. Once the freeze took hold, it snowballed, encasing Earth in a shell miles thick. For 58 million years, the Sturtian reigned, followed by a brief thaw, just 10 million years of reprieve, before the Marinoan glaciation plunged the planet back into ice for another 5 to 15 million years. Beneath this frozen veneer, life clung to existence. Bacteria thrived near geothermal seeps, their microscopic empires, fueled by chemical whispers from the deep. Algae drifted in pockets of meltwater, and primitive single-celled organisms pulsed in the gloom. But something astonishing was brewing. In the isolation of this icy prison, ecosystems became fragmented, sealed off by walls of frost. Some scientists speculate this solitude was a crucible for evolution. Cut off from rivals, certain niches fostered the first stirrings of multicellular life, tiny, fragile assemblies of cells groping toward complexity. It's a theory draped in mystery, its threads too faint to grasp fully, yet it hints at a paradox, a world of death birthing life anew. Then, abruptly, the ice relented. Around 635 million years ago, the Marinoan thaw unleashed a torrent of meltwater, flooding shallow shelves and stirring the oceans into a nutrient-rich broth. What followed was a fireworks display of biology, the Cambrian explosion. Over a mere 40 million years, a blink in geologic time, the fossil record erupted with diversity. Trilobites scuttled across seabeds, worms burrowed through sediment, and the ancestors of every major animal group took shape. The University of California's Museum of Paleontology marks this as the dawn of complex life, a legacy born from the snowball's ashes. But how did a frozen wasteland ignite such a spark? Perhaps the isolation honed new forms, or the thaw's chaos unleashed a genetic free-for-all. The truth dances just beyond our reach. Geologists once scratched their heads at the clues. In Namibia's sun-scorched cliffs, they found limestone, rock forged in tropical seas, sandwiched by glacial scars. Dropstones, pebbles plucked from icebergs and dumped into marine mud, littered the record. These signs whispered of glaciers in the tropics, a puzzle that defied logic. How could ice blanket even the equator? Early skeptics balked, dismissing the snowball Earth hypothesis as fantasy. The deposits looked like cement spilled from a cosmic mixer, not the gentle layers of a warm world. Yet the evidence mounted: paleomagnetic data, charting ice near the ancient equator, deep flooding scars from the melt, until doubt gave way to awe. The hypothesis wasn't always embraced. Conceived in 1989, it stitched together decades of geologic musings, but dating the events proved a thorn. The Sturtians' 58 million year reign dwarfed the Marinoans' fleeting grip. Why the disparity? And why the mere 10 million year gap between them? Climate models, born from modern computing, offered clarity. They painted a planet where ice fed on itself, where volcanic hiccups or a CO2-starved atmosphere tipped the scales. Yet questions linger. The slush ball theory, a milder rival, suggests open oceans persisted, with CO2 building fast to hasten the thaw. But the geologic ledger disagrees. 58 million years of ice isn't a slushy footnote, and the abrupt, scorching climates that followed each snowball defy a gentle fade. Picture that post-glacial dawn, a steamy Earth, its ice retreating under a haze of volcanic gas and rising CO2. The oceans, once locked in darkness, shimmered with possibility. Life didn't just survive, it exploded, rewriting its code in a frenzy of adaptation. Alternative triggers have danced into view, like a 2005 notion that the solar system brushed a molecular cloud in the Milky Way's spiral arms, dimming the sun. Isotope tests, though, found no echo of such a cosmic waltz. The snowball's architects, tectonics, volcanoes, a reflective crust, remain the prime suspects, their fingerprints etched in stone. Could it happen again? Stand on a windswept bluff today, watching snow dust the horizon, and the question feels alive. Science offers comfort. Not soon, not in tens of thousands of years. Today's continents sprawl too wide, their drift too slow to replay Rodinia's drama. Even in harsh winters, ice sheets would halt weathering, letting CO2 climb and warm the air. A break on runaway frost. But future is a slippery word. Millions of years hence, who can say? Earth's history is a tapestry of upheaval, ice ages, eruptions, the churn of life, and the snowball Earth is but one wild thread. Step into that frozen past, if only in your mind. The air stings, the silence roars, and beneath your feet a planet holds its breath. It's not the Earth we know, with its bustling seas and green hills. This is a stranger, a ghost from eons past, whispering lessons we're still decoding. The snowball. Earth isn't just a tale of ice. It's a mirror to our fragility, a testament to life's tenacity. Without those frigid trials, would we be here pondering the stars? Science digs deeper, peeling back layers of rock and time, chasing answers to a Sisig saga that shaped us all. So here we stand, on a world that's weathered more than we can fathom. The snowball Earth reminds us, this planet wasn't always our gentle home. It's been a crucible, a battlefield, a laboratory of chance. If this journey through the ice intrigues you, give it a nod, lift your thumb to the sky. The more who join this quest, the richer it grows. Stick with us, dive into the unknown, and let's meet again where the past meets the possible. In 2003, a team of astronomers peering into the distant reaches of our solar system stumbled upon a remarkable discovery, a dwarf planet lurking in the Kuiper Belt, later christened Sedna. At the time, it held the title of the most distant known object orbiting our sun, a solitary sentinel in the cosmic wilderness. This wasn't just another rock floating in space, it was a revelation, a key that unlocked a cascade of questions and reshaped our understanding of the solar system's outer fringes. Sedna's discovery sent shockwaves through the astronomical community, and its implications were nothing short of revolutionary. For one, it played a pivotal role in dethroning Pluto from its long-held status as the ninth planet. Sedna's existence hinted that the Kuiper Belt, a vast icy ring beyond Neptune, wasn't just a cosmic afterthought, but a treasure trove teeming with secrets waiting to be unearthed. More tantalizing still, Sedna reignited an age-old debate that had simmered since the 19th century. Could there be a mysterious ninth planet hiding in the shadows, pulling strings from afar? The evidence was compelling. Out there on the ragged edge of the solar system, something massive seemed to be meddling with the orbits of smaller celestial bodies. These objects, scattered across the Kuiper Belt, weren't behaving as expected. Their paths curved and twisted, deviating from the tidy trajectories one might predict. Imagine a flock of birds suddenly veering off course, all nudged by an unseen wind. The orbits of these distant wanderers were stretched into elongated ovals, and curiously, they all tilted in the same direction, skewed by the same precise angle. This wasn't random chaos, it bore the fingerprints of a gravitational puppeteer. Enter Michael Brown and Konstantin Batygin, two astronomers who've staked their reputations on cracking this cosmic mystery. They're convinced that this unseen influencer is none other than the elusive Planet 9, a world perhaps 10 times Earth's mass, with a diameter 2 to 4 times our own, lurking in the darkness beyond Neptune. For Brown and Batygin, Sedna wasn't just a discovery, it was a breadcrumb leading to a prize that could define their careers. Their calculations, based on the peculiar dance of Sedna and a handful of other Kuiper belt objects, suggest a planet so massive it warps the fabric of space around it, tugging at everything in its reach, but not everyone sold on the idea of a planet. Some scientists propose a more exotic suspect, a primordial black hole. Now, don't picture the colossal, star-gobbling behemoths at the hearts of galaxies. This would be a tiny, dense relic from the dawn of time, perhaps no bigger than a bowling ball or even a tennis ball, yet packing a gravitational punch far out of proportion to its size. These hypothetical objects, dubbed primordial black holes, could be sprinkled across the universe like cosmic Easter eggs, remnants of the Big Bang's chaotic birth. The notion of primordial black holes first flickered to life in the 1960s, thanks to Soviet physicists Yakov Zeldovich and Igor Novikov. They imagined a universe just seconds old, a searing, dense speck born from the Big Bang some 13.7 billion years ago. In those fleeting moments, the cosmos was a cauldron of unimaginable heat and pressure, a primordial soup where the rules of physics were still taking shape. Then came a pivotal split. Gravity peeled away from the other fundamental forces, electromagnetism, the weak nuclear force, and the strong nuclear force, ushering in an era known as the Planck epoch. This epoch lasted a mere fraction of a second, a blink in cosmic terms, yet it set the stage for everything that followed. The universe was still microscopic, measured in Planck lengths, unfathomably small units, but it brimmed with potential. As it expanded and cooled, pockets of extreme density emerged amid the turmoil. In these hotspots, gravity could have clumped matter so tightly that it collapsed into tiny black holes, each a seed of destruction sown in the universe's infancy. Stephen Hawking picked up this thread in 1971, weaving it into a richer tapestry. He calculated that primordial black holes might range in mass from modest asteroids to hulking planetoids, or even several times the heft of our Sun. Unlike their stellar-born cousins, which form from the corpses of massive stars, these primordial oddities could be any size, their origins tied not to stellar death, but to the Big Bang's raw energy. The smallest ones, Hawking reasoned, would be long gone by now, evaporating in bursts of radiation, a phenomenon now called Hawking radiation. This self-accelerating process ends in a flash, though no one's caught such a fireworks show in the sky. Larger primordial black holes, however, could still linger. Those in the mid to heavy range, say asteroid-sized or planetoid-shaped, might lack the spin of stellar black holes, making them trickier to spot. They don't gobble up matter with the ferocity needed to form glowing accretion disks, the telltale halos that often betray their presence. Instead, they might reveal themselves subtly, bending light through gravitational lensing, a cosmic magnifying glass effect that warps the paths of distant stars' rays. Hawking speculated that our galaxy, the Milky Way, could be peppered with these ancient relics. If they formed in droves during the Big Bang's early chaos, some should still haunt the cosmos today. Yet, despite decades of searching, no one's nabbed definitive proof. Primordial black holes remain a tantalizing what if, a hypothesis dangling just out of reach. If they do exist, though, they could unlock some of cosmology's thorniest puzzles, starting with dark matter. Dark matter, that invisible glue holding galaxies together, accounts for about 25% of the universe's mass energy budget. It doesn't glow, reflect, or radiate, yet its gravitational pull shapes the cosmos. In 1994, Russian astrophysicists Pavel Ivanov, Pavel Naselsky, and Igor Novikov floated a bold idea. What if primordial black holes, with masses around a tenth of our sun's, were plentiful enough to explain this unseen heft? Even if they're not the whole story, these compact enigmas could contribute significantly to the dark matter tally, offering a concrete candidate for a mystery that stumped scientists for generations. But the intrigue doesn't stop there. Primordial black holes might also explain stranger phenomena, like the merging of black hole pairs. Stellar evolution models struggle to account for such duos. If two massive stars birth black holes, one typically collapses first, siphoning material from its partner and stunting its growth. Yet we've detected these mergers via gravitational waves. Could they be primordial black holes, never stars to begin with, drifting together since the universe's youth? Or take the supermassive black holes, squatting in galactic cores? Conventional wisdom says galaxies birthed these giants, feeding them over eons. But what if it's the other way around? What if primordial black holes, seated in the Big Bang, acted as gravitational anchors, gathering matter and sparking galaxy formation? Quasars, blazing beacons powered by supermassive black holes, have been spotted at distances implying they existed just 12.9 billion years ago, when the universe was barely a billion years old. Their staggering masses, hundreds of times greater than the Milky Way's central black hole, defy easy explanation. How could they grow so vast so fast? Here's where primordial black holes shine as cosmic accelerators. Picture them as Big Bang seedlings, their gravity hastening the clumping of matter into stars and galaxies. The youngest galaxies we've observed formed a mere 400 million years after the Big Bang. Far too quickly, some argue, for standard star formation alone. A scattering of primordial black holes could have turbocharged the process, their pull sculpting the early universe into the sprawling tapestry we see today. Back in the Kuiper Belt, Brown and Batigan's Planet 9 hunt echoes these grander questions. Their evidence hinges on Sedna and 6 other far-flung objects, whose orbits align too neatly to be mere coincidence. These bodies trace elliptical paths, skewed perpendicular to the solar system's plane, as if herded by a massive shepherd. The duo's math points to a Neptune-sized world, or perhaps a black hole the size of a grapefruit, with a mass 10 times Earth's. Light bending near its suspected location adds fuel to the black hole theory, though a snapshot from a telescope remains the holy grail. Deep within the enigmatic heart of a black hole lies a puzzle that defies comprehension: the singularity. This infinitely dense point twists the fabric of space-time into a knot so tight that our logical frameworks unravel. Worse still, it flouts some of the universe's most sacred rules. The thorniest issue revolves around how black holes handle information, the quantum blueprints describing everything they devour. Physicists cling to a bedrock principle: information cannot, must not, be destroyed. Yet when a singularity swallows it whole, that's precisely what seems to happen. This conundrum, known as the black hole information paradox, is a cosmic riddle of monumental stakes. But let's hold off on that for a moment and dive into something equally mind-bending: the Planck star. Picture a Planck star as a daring alternative to the singularity, a theoretical twist born from the Big Bounce hypothesis. This isn't your standard cosmic tale of a one-and-done Big Bang. Instead, imagine the universe as a phoenix, endlessly rising from its own ashes in a cycle of collapse and rebirth. The Big Bang we know? It might just be the latest chapter, not the opening scene. Before our universe stretched into being, another could have existed, one that ballooned to its limits, then crumpled under its own weight, only to explode anew. Its reincarnation on a galactic scale, a story of perpetual renewal. Curious for more? There's a video diving into this cosmic loop. Check the link up top on the right. Here's how it plays out. The universe expands until it hits a tipping point, a moment when the average density of space-time reaches a critical threshold. Then, the tide turns. Expansion halts and collapse begins, squeezing all matter into a super-dense state, something eerily akin to a black hole's singularity. But the Big Bounce theory doesn't let it end there. When matter compresses to the Planck scale, the tiniest conceivable unit in physics, an extraordinary rebound kicks in. This isn't mere speculation. It's a lens that could reshape how we view black holes entirely. What if the collapse of a stellar core doesn't doom it to an infinitely dense singularity, as we've long assumed for stellar mass black holes? Suppose instead that quantum pressure steps in, halting the plunge. Think of it like the force that keeps an electron from crashing into an atom's nucleus, a subtle but mighty resistance. This isn't as wild as it sounds. After all, neutron degeneracy pressure can stall a star's collapse, leaving behind neutron stars or pulsars, while electron degeneracy does the same for sun-sized stars, birthing white dwarfs. Scale that up and quantum effects might stop matter from hitting infinite density, not just in stars but across the cosmos. In this grander picture, the Big Bounce doesn't wait for the universe to shrink to Planck length. It triggers when the energy density of matter hits Planck scales, the densest possible state in physics. The universe doesn't just teeter on the edge, it springs back, a cosmic trampoline launching a new era. For black holes, this could mean singularities aren't the endgame. Instead, they harbor Planck stars, compact quantum-defying objects that rewrite the script. So, what would a Planck star look like to us? The clue's in the name. These entities would be staggeringly small, dwarfing even an atom, squeezed down to Planck dimensions. But their real magic lies in time. Time, that relentless river, doesn't flow the same for everyone. On Earth's surface, it ticks slightly differently than in low orbit, a subtle shift. Near massive stars, planets, or black holes, the difference grows stark. As light nears a black hole's event horizon, the boundary beyond which nothing escapes, time slows to a crawl. Inside, some of the brightest minds speculate it might freeze altogether. From the outside, though, you'd never guess. It's a head-scratcher, so let's borrow a scene from Interstellar to simplify. Remember the water planet orbiting a black hole? An hour there stretched into decades elsewhere. The first astronaut to land might have touched down 10 years prior, yet for her, mere hours passed before the next crew arrived, her beacon still blinking, though her transmissions had long faded. A Planck star might live a similar dual life, a fleeting instant in its own frame, crossing its tiny expanse at light speed, yet enduring for millions or billions of years to an outsider, coexisting with the black hole itself. Perhaps it's not a star in the classic sense, more a burst of light unleashed as the black hole dies. This brings us full circle to the information paradox. Replace the singularity with a Planck star, and the problem might dissolve. Black holes gradually shed mass via Hawking radiation, a slow leak of energy over eons. Eventually, the Planck star within could expand, releasing all the trapped information in a final flourish. Some theorists even suggest these stars emit a detectable quantum gravitational signal, with wavelengths around 10 to 14 centimeters, tiny enough to hint at their presence in gamma-ray signatures. Could we have already glimpsed one, misfiled in the data? Carlo Rovelli, a co-creator of the Planck star idea, thinks it's testable. The spectra of black hole explosions, he argues, shift based on distance from Earth. Match those patterns to fast radio bursts, and the theory might hold water, or it might not. So far, no smoking gun, but the universe loves a good tease. Imagine standing on the edge of a cosmic precipice, peering into the abyss of a dying black hole. As its mass dwindles, the Planck star inside swells, a ticking clock counting down to revelation. What might we see? A flicker of gamma rays, perhaps, or a whisper of light from a realm where time itself bends. Rovelli's bet isn't just a hunch, it's a challenge to scour the skies with tools like the Fermi Gamma Ray Space Telescope, hunting for those telltale bursts. Fast radio bursts, those enigmatic blips we've caught in recent years, could be Planck stars winking at us from the void. Or they could be something else entirely, cosmic static teasing our curiosity. Speaking of teases, don't confuse Planck stars with primordial black holes. Those Big Bang relics are a different beast, tied to Planck length, not energy density. A video on those? Maybe, if you clamor for it in the comments. For now, let's pivot to another cosmic oddity that's equally spellbinding: boson stars. These aren't your twinkling night sky fixtures, they're hypothetical marvels that stretch the imagination. To grasp boson stars, we need a quick dip into particle physics. Don't worry, we'll keep it light. The Standard Model splits the universe's building blocks into two camps: fermions, the stuff of matter, and bosons, the couriers of forces. Fermions are loners, one per slot in space, while bosons are party animals, piling up without limit. We know 6 elementary bosons, like the W and Z bosons of weak interactions, which flip particles from one type to another. But the headliner is the Higgs boson, discovered amid fanfare at CERN. It's the VIP that gifts particles their inertial mass, the kind that resists a shove, not the gravitational pull. A quantum theory marrying inertia and gravity, still a pipe dream. Now, imagine a stable swarm of bosons, bound by their own gravity into a self-sustaining system. That's a boson star, a cosmic outlier unlike any star we know. They might mimic a sphere, like their fiery cousins, but some theorists picture them flattening into a colossal donut under centrifugal spin. Trouble is, none of the bosons we've pinned down, like the Higgs, fit the bill. They're either too unstable or massless to clump into stars. But yet is the key word. Undiscovered bosons like the elusive graviton, hypothetical carrier of gravity, could change the game. Gravitons might boast both mass and stability, the perfect recipe for boson stars. A graviton deep dive. Drop a yes below if you're game. If gravitons exist, boson stars could have burst into being post-Big Bang, collapsing from primordial gravity wells. Unlike fermion-based stars, they wouldn't shine. They'd be transparent, ghostly orbs adrift in space. Their only giveaway? A gravitational tug strong enough to bend light or nudge orbits. When they grow too bloated, they might collapse, blasting out radio photons, a clue that sparked the theory. But without a known boson to build them, they stayed off the radar until tools like LIGO and Virgo, gravitational wave hunters, came online. Boson stars' waves would ripple differently than those from stellar giants, offering a shot at detection. Picture a boson star drifting silently through the cosmos, a shadow among shadows. Its collapse wouldn't be a fiery supernova, but a quiet implosion, a radio whisper echoing across light years. LIGO's sensors might catch that tremor, a vibration distinct from the violent clashes of neutron stars or black holes. And if gravitons are real, these stars could be legion, born in the Big Bang's afterglow, clustering in the dark corners of galaxies. Some speculate they'd swarm near galactic centers, masquerading as the supermassive black holes we've pinned there. Others see them as lone wanderers, bending starlight in subtle arcs we've yet to decode. Where to look? The cosmos is vast, but galactic cores are prime suspects. A boson star there could explain the wild antics of active galactic nuclei, those blazing hubs of energy. Or maybe they're scattered across the void, silent until they burst. Unlike Planck stars tied to black hole deaths, boson stars could stand alone, relics of a universe still spilling its secrets. Detecting them might mean sifting through gravitational wave data, teasing apart the hum of the cosmos for a note no one's heard before. Imagine the thrill. Pinpointing a boson star's echo could unveil new particles, rewriting physics from the ground up. The universe isn't done surprising us. Planck stars, boson stars, quark stars, they're paper dreams for now. But the evidence mounts. Fast radio bursts, gravitational ripples, gamma-ray flickers, each could be a breadcrumb to the next big find. Once exoplanets and galaxies awed us, now they're old news to a skeptical age. Yet the cosmos keeps its aces up its sleeve, daring us to peek. Will Planck stars solve the information paradox? Could boson stars anchor galaxies? The answers hover just out of reach, but the hunt, fueled by math, telescopes, and sheer wonder, presses on. Consider the stakes. A Planck star's discovery could upend our view of black holes, proving information endures beyond the event horizon. Boson stars might crack gravity's code, linking it to the quantum realm. Each breakthrough would ripple beyond science, stirring philosophy and imagination alike. Are we on the cusp of spotting one? Picture a telescope catching a gamma flicker, or LIGO tracing a wave to a donut-shaped ghost. The universe doesn't yield easily, but its whispers grow louder. What's your bet on the next revelation? Let's hear it. Imagine a cosmic riddle so elusive it's been dubbed the invisible puppeteer of the universe, dark matter. This mysterious substance doesn't glow, flicker, or whisper its presence through light, yet it wields a gravitational pull that keeps galaxies from spinning apart. Scientists have chased its trail for decades, pinning their hopes on everything from exotic particles to unseen dimensions. But what if the answer, or at least part of it, lies in something as strange and captivating as a boson star? Yes, those hypothetical orbs of pure bosons might just be a piece of the dark matter puzzle, and a recent discovery has sent ripples of excitement through the astronomical community. It all started with a gravitational wave, a faint tremble in the fabric of space-time detected in an event tagged GW19521. When the signal first washed over Earth's observatories, experts buzzed with the obvious guess. Two massive black holes, weighing in at 66 and 85 times the sun's mass, had smashed into each other in a cataclysmic dance. The idea fit neatly. Black holes are the heavyweight champs of cosmic collisions after all. But as researchers dug deeper, poring over the data with furrowed brows and humming computers, cracks appeared in that story. The numbers didn't quite align. Something was off. Then came a bold twist. What if this wasn't a black hole tango at all, but a clash of boson stars, ghostly spheres woven from ultralight bosons. Now, boson stars aren't your average celestial celebrities. They don't blaze with nuclear fire or twinkle in the night sky. Picture them instead as ethereal bubbles lacking a solid core, transparent to light, and utterly invisible to the naked eye. Sound familiar? That description could double as a black hole's resume. Both are compact, both wield gravity like a maestro, and here's the kicker. Some boson stars might even sport a shimmering ring of plasma, a glowing donut encircling a dark heart. It's eerily similar to the accretion disk that swirls around a black hole, painting a portrait of cosmic mimicry that's hard to ignore. From millions of light years away, could we really tell them apart? At first glance, you'd think not. Black holes have a defining trait: the event horizon, that invisible line where light and matter check in but never check out. Boson stars, though, lack this boundary. No trapdoor to oblivion, just a dense, gravity-warped blob. But distinguishing them isn't a hopeless quest. Scientists turned to a high-tech crystal ball, computer simulations. They modeled the dynamics of that plasma ring around a boson star and pitted it against the behavior of a black hole's accretion disk. The results? A revelation. The shadow cast by a boson star, a silhouette carved out by its gravity-bending light, is noticeably smaller than the gaping maw of a black hole shadow of the same mass. This shadow game became a cosmic litmus test. Take GW9521's aftermath. Researchers calculated the mass of the colliding objects and clocked the speed of the gas swirling around them. The shadow loomed too large, too pronounced to belong to a boson star. Verdict: black holes, not boson imposters. But here's where it gets juicy. This doesn't slam the door on boson stars. It just means we've got a sharper tool to spot them. What if some of the black holes we've cataloged, those dark titans we've crowned as cosmic royalty, are secretly boson stars in disguise, pulling a fast one on our telescopes? The implications are dizzying. If boson stars are real, they could be dark matter's missing link. We've long pictured dark matter as a shadowy sea of particles, too aloof to shine yet heavy enough to anchor galaxies. Boson stars fit the bill. Unseen, gravitationally potent, and potentially numerous. Some theorists go further, whispering that these stars might be forged from gravitons, those still undiscovered messengers of gravity. If true, it's a game changer. Either dark matter isn't what we thought, or gravity itself is tangled up in its essence. Suddenly, the universe feels less like a solved equation and more like a thriller, with a twist ending still unwritten. Let's rewind and paint the scene. The GW19521 signal wasn't just a blip, it was a cosmic drum roll. Detected by the Laser Interferometer, Gravitational Wave Observatory, LIGO, and its partner Virgo, it rippled through space-time like a pebble dropped in a pond. At first, the black hole theory held sway because it's the go-to playbook for such events. Two stellar corpses, born from exploded stars, spiral inward over eons, their orbits tightening until they merge in a flash of warped reality. But the masses, 66 and 85 solar masses, raised eyebrows. Stars massive enough to birth such black holes should have shed too much material in their fiery youth to fit the profile. Enter the boson star hypothesis. No stellar origins needed, just a swarm of bosons clumping together in the universe's early chaos. To test this, scientists didn't just lean on gravitational waves. They zoomed in on the aftermath, the light and gas left behind. Black holes often leave a blazing trail as they gobble up nearby matter, their accretion disks glowing like neon signs. Boson stars, though, play it cooler. Their plasma rings, if they have them, shimmer with a subtler flare. Simulations showed that a boson star's shadow wouldn't stretch as wide, its gravitational lens less distorted than a black hole's. When GW1952's data rolled in, the shadow's size tipped the scales. It wasn't a boson star's delicate footprint, it was the hulking mark of a black hole. But don't write off boson stars yet. This one case doesn't bury the idea, it sharpens our focus. Imagine a sky dotted with these invisible mimics, some masquerading as black holes, others lurking undetected. If they're out there, they could be plentiful, relics from the Big Bang, forged when gravity first flexed its muscles. And if they're gravitons in disguise. That's a plot twist that could rewrite physics. Dark matter might not be a swarm of particles, but a legion of boson stars, their gravity weaving the cosmic web we've puzzled over for a century. The chase is on. LIGO and Virgo keep their ears to the universe, listening for the next ripple. Telescopes scan for shadows that don't quite fit the black hole mold, subtle clues in the bending of starlight or the hum of radio waves from a collapsing boson star. Each observation peels back another layer, teasing us closer to the truth. Are boson stars the dark matter we've sought? Or just one thread in a tapestry of unknowns? Maybe they're both, partners in a cosmic conspiracy, hiding in plain sight. This isn't the end of the story, it's the opening act. The universe loves a good mystery, and boson stars are its latest cliffhanger. They challenge us to rethink what we know, to peer beyond the obvious and question the shadows. Could they unlock dark matter's secrets? Might they bridge gravity and the quantum world? The answers are out there, twinkling in the void, waiting for us to catch up. So buckle up. The most thrilling chapters lie ahead. Picture yourself stargazing on a clear night, wondering if those unseen forces are boson stars winking back. Excited? You should be. The cosmos is a stage and the spotlight's just warming up. Stay curious, keep exploring, and let's unravel this together, because the best is yet to come. Someone wise once remarked, "The cosmos is the grandest art gallery imaginable." It's a statement that's hard to argue with, especially when you gaze at the breathtaking vistas captured by our telescopes, swirling galaxies, shimmering nebulae, and stars blazing in every hue of the cosmic palette. The universe is a sprawling masterpiece, vast beyond comprehension, endlessly stretching into the unknown, shattering every boundary our minds can conceive. It's a place of awe, mystery, and relentless beauty. But like all things, even this grand exhibition must one day draw to a close. Imagine a future so distant it dwarfs every apocalyptic blockbuster Hollywood has ever churned out. Picture a universe where the last living stars have flickered out, their radiant flames extinguished. No new stars ignite in the void. Creation has stalled, the cosmic nursery long since abandoned. What remains is a desolate expanse dotted with black holes of every size and mass, silently evaporating into nothingness through the eerie quantum magic of Hawking radiation, a process where these gravitational titans leak particles into the abyss. The once vibrant tapestry of the cosmos has unraveled, leaving only shadows of its former glory. And what of the stars that once painted the night sky with light? Their remnants linger as white dwarfs, dim, cooling husks of what they used to be. Gone are the majestic constellations, the glowing clouds of gas and dust, the radiant beacons that guided ancient dreamers. Darkness creeps in, an unyielding tide that seeps into every corner, swallowing the universe whole. It's a somber scene, a requiem for infinity, but hold that thought. Let's not linger in the gloom just yet. Instead, let's rewind and explore the fascinating characters in this cosmic drama, the white dwarfs. White dwarfs are the retirees of the stellar world, and they've got quite a story to tell. If you've ever tuned into our videos, or if you're new here, welcome aboard. You might recall we've covered these celestial relics before. Stars, you see, are not static. They evolve, their fates dictated by a key player, mass. A star's mass determines whether it'll exit the stage with a bang or fade away with a whisper. Take stars like our sun, modest yellow dwarfs that don't quite qualify for the heavyweight division. These stellar middleweights spend their lives, about 11 billion years for the sun, quietly fusing hydrogen into helium, a slow burn that sustains their glow. But even the steadiest candle eventually gutters. When the fuel runs low, these stars swell into red giants, their outer layers puffing up like a cosmic balloon. Think of Aldebaran, the fiery eye of Taurus, a red giant familiar to stargazers since childhood. Then, in a dramatic finale, they shed their outer shells and collapse inward, compressing into a dense, glowing ember, a white dwarf. Let's zoom in on a real-life example. Sirius B, the nearest white dwarf to Earth, a mere 8.6 light-years away, practically next door in cosmic terms. Once a robust star, Sirius B shed its outer layers some 120 million years ago, leaving behind a core no larger than Earth, but packing a mass close to the Sun's. It's a stunning transformation. A star that once blazed brightly, now reduced to a faint, shrinking spark. Structurally, a white dwarf is a marvel, a ball of electron-degenerate matter, a soup of plasma so dense that a teaspoon of it weighs as much as an elephant. Without a fusion furnace to keep it warm, it cools slowly, radiating its leftover heat into the void. But the story doesn't end there. Given enough time, trillions of years, mind you, a white dwarf might fade further, transitioning into a black dwarf. These enigmatic objects barely glow, if at all, their light too feeble to pierce the darkness. For years, astronomers thought black dwarfs were the final chapter for stars like these, the ultimate endpoint of stellar evolution. But hold your telescopes. There's more to this tale, and we're about to unravel it. Black dwarfs are the underdogs of the cosmic cast, elusive and misunderstood. Unlike their white-hot predecessors, they emit little to no visible light, making them ghostly figures in the universe's lineup. A key condition for their existence is the absence of accretion. No more siphoning gas or dust from their surroundings to fuel their glow. They're cut off, left to cool in isolation. Here's the catch. You won't find black dwarf plastered across scientific journals, and no, it's not because of some interstellar conspiracy. It's simpler than that. Our universe, at roughly 13.8 billion years old, is still a spry youngster by cosmic standards. White dwarfs take billions of years to cool to the frigid temperatures, around 5 Kelvin, just above absolute zero, needed to become black dwarfs. The coldest white dwarfs we've spotted hover around 4,000 Kelvin, still too toasty to cross that threshold. In short, the universe hasn't had time to churn out a significant population of black dwarfs. They're a future phenomenon, a preview of what's to come. But what will come? The universe isn't an endless well of star-making material. Interstellar gas, the raw stuff of creation, is finite. As it dwindles, star birth will cease, and the slow march of cooling white dwarfs will give way to a new regime, the age of black dwarfs. These objects have a mass ceiling known as the Chandrasekhar limit, about 1.4 times the Sun's mass. It's the tipping point where the pressure of degenerate electrons balances gravity's crushing grip. Beyond this limit, a star's fate veers toward neutron stars or black holes. But for black dwarfs, this boundary sets the stage for some wild possibilities. Black dwarfs might seem like the end of the line, but the universe loves a plot twist. These cold, quiet relics could have a few tricks up their sleeves, depending on forces like dark matter and quantum quirks. Let's explore two jaw-dropping scenarios for their distant future. In the first act, black dwarves might tap into dark matter, if it exists, to prolong their twilight years. Picture them as cosmic scavengers, sipping on this mysterious substance to stave off oblivion. But even dark matter can't stop the clock forever. Protons, the building blocks of matter, face an existential dilemma: decay or endure. If protons decay, a big if in physics, black dwarfs could unravel over an unimaginable timescale, a decillion years, that's 10 years, a number so vast it's a 1 followed by 33 zeros. As they decay, these dwarfs transform into iron-56, a stable isotope, becoming what astronomers call iron stars. These metallic husks could linger for an eternity, think 10^76 years, a 1 with 76 zeros, before collapsing into black holes under their own weight. From there, Hawking radiation takes over, evaporating them over an unvigintillion years, 10^66. It's a slow, drawn-out exit, a cosmic tragedy stretching across eons. Not exactly a blaze of glory, but a fittingly quiet end for such understated players. Now buckle up for the second act, because this one's a showstopper. Quantum mechanics throws a curveball with a phenomenon called quantum tunneling, where particles sneak through barriers they shouldn't be able to cross. Inside a black dwarf, this could spark spontaneous nuclear fusion, even without the energy to sustain it. Over countless millennia, fusion products pile up, choking the dwarf's core until it can't take it anymore. Then, bam, a black supernova erupts. Unlike the dazzling supernovae of massive stars, which birth neutron stars or seed new stellar nurseries, this explosion is a swan song. Only about 1% of black dwarfs, those near the Chandrasekhar limit, might pull off this feat. It's a rare, cataclysmic encore, a final flare in a universe grown dark and cold. These blasts could be the last fireworks in the cosmic sky, signaling the end of an era. Step back and take it all in. Imagine a universe where black dwarfs dominate, relics of a time when stars ruled the heavens. The once bustling cosmos fades into a wasteland of silence and shadow. Regular supernovae leave behind legacies, neutron stars, black holes, or the seeds of new stars. But black supernovae, they're the endgame, a final gasp before the void claims everything. Ice and darkness reign supreme, an all-consuming stillness that blankets infinity. It's a chilling vision, but don't despair just yet. These are hypotheses, cosmic what-ifs based on our best calculations. And here's the kicker. This fate won't unfold for something like 10,000 years. A Googleplex, a number so absurdly large it defies imagination. Humanity has plenty of time to chase its dreams, explore the stars, or, let's be real, bicker its way into oblivion. Either way, the universe's grand finale is a long way off. So why not marvel at the journey instead? Let's lighten the mood with a detour through the universe's gallery of wonders. First stop, the Sombrero Galaxy, a spiral beauty in Virgo, 29 million light-years from Earth. Its elegant disk and glowing bulge hide a secret, a supermassive black hole weighing in at 1 billion solar masses. Next, meet NGC 1277, a compact lenticular galaxy in Perseus, 220 million light-years away, packing a black hole 17 billion times the Sun's mass. And then there's Holmberg 15A, a colossal elliptical in Cetus, with a central beast estimated at 10 billion solar masses. These galactic titans share a common trait. At their hearts lurk supermassive black holes, gravitational juggernauts shaping their domains. We've cataloged dozens of these monsters, each a testament to the universe's penchant for extremes. But how did they get so massive so fast? Some formed less than a billion years after the Big Bang, a puzzle that's kept astronomers scratching their heads. To crack this mystery, let's travel back to the universe's infancy, when the first stars, population 3 stars, ignited. These pioneers were forged from primal hydrogen and helium, with no heavier elements to complicate their chemistry. They were giants, hundreds of times the sun's mass, burning hot and fast. Within a million years, they exhausted their fuel, exploding as hypernovae and collapsing into black holes, seeds for something bigger. But what if some didn't collapse outright? Enter the quasi-star, a hypothetical behemoth unlike anything we see today. Not to be confused with quasars, those blazing beacons powered by black holes. Quasi-stars were massive stars with a twist, a black hole core. Picture a star 10 billion kilometers wide, over 1,000 times the sun's mass, shining 100,000 times brighter. Compared to titans like Scuti or Stephenson 2-18, quasi-stars were cosmic colossi. Their black hole hearts devoured their interiors, growing into the supermassive monsters we see today. It's a wild theory, but it might just explain the early giants lurking in galactic cores. We're just beginning to sketch humanity's chapter in this vast saga. We've decoded much about the universe, how stars live and die, how black holes warp reality, but countless mysteries remain. The origins of supermassive black holes are a tantalizing riddle, one of many we'll tackle in time. For now, let's revel in the spectacle, a universe brimming with wonders, from fading dwarfs to galactic heavyweights, all part of an epic unfolding over billions of years. So what's next? Hit that thumbs up, subscribe if you haven't, and ring the bell for more cosmic adventures. The universe isn't done with us yet, and neither are we. Until next time, keep your eyes on the stars. Imagine a star so colossal it could swallow our solar system whole, stretching its fiery tendrils far beyond Pluto's lonely orbit. Picture a behemoth with the mass of a small globular cluster, a bustling congregation of stars, and a brilliance rivaling that of a modest galaxy. This, my friends, is a quasi-star, a celestial titan that defies everything we know about the twinkling lights above. Its surface temperature, a sizzling 10,000 Kelvin, might not sound jaw-dropping at first blush. After all, it's only about twice as hot as our sun. But don't let that fool you. This isn't your average stellar neighbor. This is a cosmic enigma, a star with a secret so wild it rewrites the rules of the game. What sets quasi-stars apart isn't just their gargantuan satiapikish. It's what lurks within. Typical stars, like our sun, have cores, where nuclear fusion churns out energy, fusing hydrogen into helium in a fiery dance that keeps them shining for billions of years. But quasi-stars? They've taken a detour down a darker, stranger path. At their heart lies not a fusion furnace, but a black hole, a gravitational monster that powers the star in a way no ordinary stellar engine ever could. Before you raise an eyebrow, let's be clear. Quasi-stars are purely hypothetical. They're the stuff of scientific speculation, dreamt up to solve some of the universe's biggest mysteries. Yet their story is so tantalizing that astronomers can't help but wonder, could these giants have once roamed the cosmos? Not long ago, scientists began eyeing quasi-stars as potential ancestors of the supermassive black holes we see today, those titanic voids at the centers of galaxies, with masses stretching into the billions of suns. To understand how they might come to be, let's rewind to the universe's wild, youthful days, when chaos reigned and the seeds of creation were just taking root. Picture vast clouds of gas, swirling soups of hydrogen and helium, drifting through the primordial void. These are the cradles of stars, where gravity starts its slow, relentless work. From these clouds emerge protostars, awkward, embryonic blobs that haven't yet found their footing. They're not hot enough to spark fusion, not yet full-fledged stars, but they're growing fast, gobbling up gas and dust from their surroundings, rounding out into spheres as they bulk up. Most protostars follow a familiar script. Their cores heat up, pressure builds, and eventually fusion ignites, birthing a star like our sun. But for a select few, those rare, oversized oddballs, things take a dramatic turn. If the center of one of these massive protostars collapses under its own weight, it doesn't just fizzle out. It forms a black hole. Now, you might think, wait a second, a collapse into a black hole? Wouldn't that blast the whole star apart, leaving nothing but a cosmic mess? Fair question. In a typical stellar demise, that might be true. Think of a supernova shredding its outer layers into a dazzling nebula. But quasi-stars are different. Their sheer mass is their shield. Even as their core implodes into a black hole, their outer layers hold firm, wrapped around this newborn singularity like a protective cloak. The black hole doesn't destroy the star, it feeds it. Siphoning matter from the surrounding gas, it radiates heat and energy, keeping the quasi-star aglow. It's a symbiotic relationship, a stellar beauty with a ravenous beast at its core, sustaining each other for about 7 million years. To keep this cosmic duo humming, the black hole has to eat big, about 14% of the sun's mass every year. That's a feast of gas and dust, funneled into an accretion disk that spirals inward, glowing fiercely as it's devoured. But all stars, even the strangest ones, have an expiration date. When the quasi-star's outer layers finally thin out, or the black hole's appetite outstrips its supply, the star dies, leaving its dark heart exposed. What remains is a black hole, a seed that, over eons, could grow into a supermassive giant, anchoring a future galaxy. It's a mind-bending origin story, one that might explain how those monstrous black holes appeared so early in the universe's history. But here's the rub. Quasi-stars are as elusive as a whisper in a storm. They're hypothetical for the same reason Population 3 stars, the universe's first generation of stars, are hypothetical. Born in the raw, unpolished aftermath of the Big Bang, these ancient stars were made of the lightest elements, hydrogen and helium. With no metals to spice up their chemistry, they grew to sizes we can barely fathom, hundreds or thousands of times the sun's mass, burning hot and fast before exploding in spectacular fashion. Their lifespans were short, mere cosmic blinks, so finding evidence of them today is like hunting for a ghost in broad daylight. Quasi-stars, if they existed, would have been even rarer, fleeting anomalies in an already chaotic epoch. Could protostars really pack enough punch to become quasi-stars? Modern observations throw a wrench into the idea. Clouds with less than 1 million solar masses of material tend to birth supermassive stars. Huge, yes, but not quasi-stars. These stars might collapse into black holes too, but they lack that bizarre black hole core twist. Our understanding of star formation is still a work in progress, a puzzle with missing pieces. Yet the quasi-star theory lingers, a compelling what-if, in the quest to explain the supermassive black holes powering distant quasars, those blinding beacons trillions of times brighter than the sun. Maybe the biggest stars we've yet to discover hold the key. Now let's twist the script a bit. In videos about mega objects, we often ask, what if this thing replaced the sun? It's a classic thought experiment. Plug a giant into our solar system and watch the chaos unfold. But let's mix it up. Imagine a quasi-star doesn't replace the sun, but barges into our neighborhood, strolling in from Neptune's direction. What happens next? First off, we'd spot it long before it crashed the party. A star that bright, that massive, would light up our skies like a second dawn, growing more dazzling with every passing day. Telescopes would buzz, social media would explode, humanity would be transfixed. But this isn't a feel-good visitor. As the quasi-star barrels into the solar system, its gravity would wreak havoc. Planets, asteroids, comets, everything would be flung from their orbits like toys in a toddler's tantrum. Earth wouldn't escape the chaos. Meteoric showers would pepper our planet, a relentless barrage of rock and ice tearing through the atmosphere. The quasi-star's path would bulldoze through the outer giants, Neptune, Uranus, Saturn, Jupiter, disrupting or devouring them as it goes. Closer to Earth, its heat would turn our world into an oven. At 260 degrees C, the atmosphere would boil into steam and carbon dioxide, choking out life. Push the dial to 760 degrees C, and sulfur dioxide would join the mix, a toxic brew straight out of a nightmare. The temperature would keep climbing until Earth's crust and mantle vaporized, our planet reduced to a fleeting snack for the quasi-star's insatiable black hole. In the end, nothing would remain, just a slightly fatter black hole, drifting onward. Grim? Sure. But it's a reminder of the universe's untamed power. If you're as hooked on cosmic wonders as we are, hit that subscribe button and give this tale a thumbs up. We'd love to keep exploring the void with you. See you in the next stellar showdown. Despite mountains of research and terabytes of data, humanity's grasp of the cosmos is still in its infancy. We've cataloged stars, planets, and galaxies, but there's so much more lurking out there. Objects we've only theorized about, some we've modeled on computers, others we've barely dared to imagine. Are they real? Maybe. Maybe not. The point isn't that we're stumbling in the dark, it's that we've only just begun to shine a light. Theoretical predictions have a knack for turning into discoveries. Take Neptune. It was math, not a telescope, that pinpointed its existence. Neutron stars were dreamed up decades before we spotted their eerie glow. Today, we know of thousands of them, and that's just the start. So why not quasi-stars? Or something even weirder, like quark stars? Let's dive into that rabbit hole and see where it leads. Start with neutron stars, the cosmic leftovers of medium heavyweights. Imagine a star bigger than the sun, but not quite a titan, say up to 8 solar masses. It lives its life, fuses its fuel, and then when the tank runs dry, it goes out with a bang, a supernova. The explosion paints the sky with a nebula, a shimmering farewell. What's left behind depends on mass. If the core tips past 3 solar masses, gravity wins and it collapses into a black hole. But if it lands below that threshold, say 1.5 solar masses, you get a neutron star. These things are tiny, about 20 kilometers across, the size of a city, but absurdly dense. A sugar cube of neutron star material weighs as much as Mount Everest. In our Milky Way, they're rare gems, 1 per 1,000 regular stars. Their insides are a crush of neutrons, packed so tight that atoms as we know them cease to exist. But what if a star's mass falls into a gray zone, too heavy for a neutron star, too light for a black hole? Enter the quark star, a contender so strange it makes neutron stars look tame. Quark stars double the mystery. The name comes from quarks, the tiniest building blocks of reality. Quick primer. Quarks are the Lego bricks of protons, neutrons, and electrons coming in 6 flavors: up, down, strange, charm, beauty, and top, each with quirky traits. Their colors, red, green, blue, aren't about hue but how they interact via gluons, the glue of the subatomic world. Quirky, right? These particles are the bedrock of everything we see, and quark stars might be their ultimate showcase. Here's the gist. Neutron stars are made of degenerate neutron matter, squashed by gravity into a solid mass. But crank up the pressure, say from the star's own weight or the supernova that birthed it, and those neutrons might crack open, spilling their quarks into a soup called quark matter. This could happen just at the core or engulf the whole star, depending on the physics at play. Trouble is, we're not sure how it works. Regular quark matter is high energy, stable only under extreme heat and pressure, like the Big Bang's first moments. A fully quark star might collapse without those conditions. Unless, that is, it transforms into strange quark matter. Here's where it gets wild. If enough up and down quarks morph into heavier strange quarks, the energy drops, stabilizing the mix. Strange quark matter might even survive in space's chill, meaning a star made entirely of it could hold together. Spotting one, though? That's the kicker. They'd look a lot like neutron stars, same size, similar glow, unless their mass stands out. A quark star might tip the scales higher than a neutron star's limit, a cosmic red flag. Theories abound, but evidence, zilch, so far. Most astrophysicists peg quark stars as neutron star cousins, siblings in the stellar graveyard. But there's a twist. Enter Edward Witten, a physics titan, who posits that clumps of strange matter, relics of the early universe, float out there, maybe as dark matter. A massive star snags one, and instead of a neutron core, it births a quark star. It's a long shot, but it's the kind of idea that keeps the cosmic pot simmering. So, where does that leave us? Quasistars, quark stars. They're shadows on the edge of our vision, possibilities waiting to be confirmed or debunked. The universe is a vast, untamed frontier, and we're just scratching the surface. Every calculation, every observation brings us closer to the truth, or to more questions. That's the beauty of it. Stick around, keep exploring, and who knows? The next big discovery might be just a telescope away. Let's conjure up a vision of a star so immense it could engulf nearly the entire solar system, its fiery edges stretching far beyond Pluto's distant orbit. A celestial giant with the mass of a small globular cluster and a radiance rivaling that of a modest galaxy. This is no ordinary star. This is a quasi-star, a cosmic marvel that pushes the boundaries of imagination. Its surface burns at around 10,000 Kelvin, a temperature that might seem underwhelming at first glance. After all, it's only about twice as hot as our sun. But don't be fooled by that number alone. The quasistar's true wonder lies not in its heat, but in its sheer scale and the bizarre secret it harbors within. Unlike the familiar stars dotting our night sky, quasistars don't play by the usual rules. Most stars, like our sun, rely on a core where nuclear fusion churns hydrogen into helium, a steady engine that powers their light and warmth for billions of years. But quasistars, they've charted a wildly different course. At their heart lies not a fusion furnace but a black hole, a gravitational vortex that drives the star in a way that defies everything we've come to expect from the cosmos. Before we dive deeper, let's set the stage. Quasi-stars are purely hypothetical, figments of scientific curiosity rather than observed realities. Yet, their allure is irresistible, offering a potential clue to one of astronomy's greatest puzzles, the origin of supermassive black holes. Not too long ago, scientists began toying with the idea that quasistars might be the ancient progenitors of those colossal black holes, lurking at the centers of galaxies, some boasting masses billions of times greater than the sun's. To explore this theory, let's travel back to the universe's chaotic infancy, a time when the cosmos was a swirling cauldron of possibility. Imagine vast clouds of gas, rich soups of hydrogen and helium, drifting through the void, untouched by the heavier elements that would come later. These clouds are the cosmic nurseries where stars first take shape. From these gaseous cradles emerge protostars, clumsy and unformed, like dough rising before it's baked. They're not yet stars in the traditional sense, no fusion fires burn within, but they're growing, pulling in more gas and dust, rounding out into spheres as gravity tightens its grip. For most, the path is predictable. As their cores heat up and pressure mounts, fusion ignites, and they become proper stars. But for a rare few, the story takes a darker turn. If a protostar grows massive enough, far beyond the norm, its center might buckle under its own weight, collapsing not into a fusion core, but into a black hole. You might wonder, a black hole? Wouldn't that tear the whole thing apart? It's a fair point. In a typical star's death throes, a core collapse often triggers a supernova, blasting its outer layers into space in a dazzling farewell. But quasistars are built differently. Their immense mass acts like an anchor, holding their outer shells intact even as the core implodes. What emerges is a strange hybrid, a star with a black hole at its heart, feeding off the surrounding gas to radiate heat and light. It's a cosmic dance, a radiant giant powered by a ravenous monster, thriving together for about 7 million years. To sustain this odd partnership, the black hole must gorge itself, consuming roughly 14% of the sun's mass each year. Picture a swirling disk of gas spiraling inward, glowing fiercely as it's devoured, fueling the quasistar's brilliance. But even this strange symbiosis can't last forever. When the star's outer layers dwindle or the black hole's appetite outpaces its supply, the quasistar fades, leaving behind its dark core, a black hole poised to grow. Over unimaginable stretches of time, this seed could balloon into a supermassive black hole, anchoring a galaxy with its gravitational might. It's a bold hypothesis, one that might explain how such titans formed so early in the universe's history. Why do quasistars remain hypothetical? The answer lies in their roots, tied to the elusive population 3 stars, the first generation of stars born in the universe's primal dawn. Forged from pure hydrogen and helium, these ancient giants lacked the metals that pepper modern stars. They swelled to sizes we can scarcely comprehend, burning bright and fast before meeting explosive ends. Their lifespans were fleeting, mere cosmic moments, so finding traces of them today is like searching for a whisper in a hurricane. Quasistars, if they existed, would have been even rarer, brief anomalies in an already turbulent era. Proving their existence is a tall order, perhaps an impossible one. Were protostars ever massive enough to become quasistars? Current observations cast doubt. Gas clouds with less than 1 million solar masses tend to spawn supermassive stars. Enormous, yes, but not the black hole-hearted oddities we're imagining. These stars might collapse into black holes too, but they skip the quasi-star twist. Our grasp of star formation is still patchy, a tapestry with threads missing. Yet the idea of direct collapse lingers, a tantalizing what-if, to explain the supermassive black holes powering distant quasars, beacons trillions of times brighter than the sun. Perhaps the grandest stars we've yet to witness hold the answer. Now let's shake things up with a thought experiment. In chats about cosmic giants, we often ask, what if this replaced the sun? It's a fun way to grasp scale. Swap out our star and watch the solar system unravel. But let's tweak the script. Imagine a quasi-star doesn't replace the sun, but gate crashes our system, barreling in from Neptune's edge. What unfolds? First, we'd notice it long before it arrived. A star that massive, that luminous, would blaze in our skies, a second sun growing brighter with each passing day. Astronomers would scramble, headlines would scream, humanity would be riveted. But this visitor isn't here to play nice. As it plows into the solar system, its gravity would upend everything. Planets would wobble, asteroids would scatter, and chaos would reign. Earth wouldn't be spared. The sky would erupt in meteor showers, a relentless bombardment as displaced rocks rain down. The quasi-star would carve a path through the outer planets, Neptune first, then Uranus, Saturn, Jupiter, disrupting or swallowing them in its wake. As it nears, Earth would roast. At 260 degrees Celsius, our atmosphere would boil into steam and carbon dioxide, snuffing out life. At 760 degrees Celsius, sulfur dioxide would choke the air, a toxic shroud. The heat would climb until the crust and mantle vaporized, Earth reduced to a fleeting morsel for the quasi-star's black hole. In the end, nothing would remain, just a slightly heftier black hole drifting on. Dark stuff, right? But it's a glimpse of the universe's raw power. If you're hooked on cosmic tales like this, smash that subscribe button and toss us a thumbs up. We'd love to keep exploring the void with you. Catch you in the next stellar saga. Despite stacks of papers and terabytes of data, our knowledge of the cosmos is a mere speck in the grand scheme. We've mapped stars and galaxies, but countless mysteries linger, objects we've theorized, modeled, but never seen. Some exist on paper, others in wild what-ifs. Does that mean we're clueless? Hardly. It means we're just getting started, peering into a universe brimming with secrets. Theoretical leaps often pave the way for discovery. Neptune was a math problem before it was a planet. Neutron stars were predicted long before their pulses lit up our detectors. Now, we've tallied thousands of them, and that's just the tip of the iceberg. So why not quasi-stars? Or stranger still, quark stars? Let's dive into that cosmic riddle and see what shakes loose. Picture a neutron star, a stellar remnant born from a medium heavyweight, say up to 8 times the sun's mass. It lives its life, burns its fuel, and then explodes in a supernova, leaving a nebula as its farewell gift. What remains depends on mass. If the core tops 3 solar masses, it collapses into a black hole. But if it's lighter, around 1.5 solar masses, it becomes a neutron star. These are tiny, just 20 kilometers across, but pack a punch. A teaspoon of their matter weighs billions of tons. In our galaxy, they're rare, 1 per 1,000 regular stars, crushed neutron husks glowing faintly in the dark. But what if a star's mass lands in a murky middle ground, too heavy for a neutron star, too light for a black hole? It's a cosmic limbo, neither here nor there. That's where quark stars step in, strangers even among the strange. They're twice as mysterious as neutron stars, named for quarks, the tiniest Lego bricks of reality. Quick rundown. Quarks build protons, neutrons, and electrons, coming in 6 flavors: up, down, strange, charm, beauty, top, each with its own flair. Their colors, red, green, blue, aren't hues but quantum quirks tied to gluons that bind them. These specks underpin everything, making quark stars a tantalizing prospect. Here's the scoop. Neutron stars are dense neutron blobs, squashed by gravity into a solid mass. Ramp up the pressure, maybe from the star itself or its supernova birth, and those neutrons might split, spilling quarks into a soup called quark matter. This could stay confined to the core or swallow the whole star, depending on the physics. Problem is, we're not sure. Regular quark matter is high energy, stable only in extreme heat and pressure, like the Big Bang's early chaos. A pure quark star might unravel without that, unless it flips to strange quark matter. If up and down quarks morph into heavier strange quarks, the energy drops, stabilizing the mix. Strange quark matter might endure in space's chill, meaning a star made of it could hold steady if it converts fast enough. Spotting one? Tricky. They'd mimic neutron stars, size, glow, unless their mass betrays them. A quark star might outweigh a neutron star's limit, a cosmic giveaway. Yet here's the kicker. Most scientists aren't ready to toss the quark star idea into the cosmic trash bin. They're optimists at heart, betting that these elusive stars are out there, waiting to be unmasked. They envision a universe where quark stars twinkle faintly, hiding in plain sight among their neutron star cousins. But not everyone's on board. The skeptics, those hard-nosed realists, raise their hands and point out the cracks in the theory. They argue that the leap from neutron matter to quark matter is a leap too far, a bridge we haven't figured out how to cross. Physics at this level is a murky swamp, barely explored, and quarks don't make it easy. Think about it. Quarks are the tiniest specks of reality, so small we can't pluck them out and study them solo. They're locked in tight-knit groups, bound by gluons, and teasing apart their behaviors like trying to solve a puzzle with half the pieces missing. Can they even form stable structures, big enough to make a star? Scientists shrug. The math is mind-bending, the experiments are limited, and the answers slip through our fingers like cosmic sand. From an observational standpoint, it's no picnic either. A quark star, if it's out there, would look frustratingly similar to a neutron star. Same size, same faint glow, same spinning dance. Spotting the difference is like trying to pick out a single stranger in a crowd of... If quark stars do exist, they're rare beasts, especially in our Milky Way. They'd occupy a razor-thin niche, sandwiched between the formation of neutron stars and black holes, a Goldilocks zone of stellar evolution where conditions have to be just right. Too light, and you get a neutron star. Too heavy, and it's a black hole. Quark stars would be the picky middle child, demanding a precise balance of mass and pressure. That rarity makes them a needle in the cosmic haystack, a challenge that pushes astrophysics to its limits. Studying quark matter isn't just a step up, it's a leap into a new frontier, a realm where our tools and theories stretch thin. Right now, the evidence is a whisper, not a shout. We've got tantalizing hints, but no smoking gun. That leaves the door wide open, both for believers and doubters. Every theory that says maybe not has as much right to the stage as the ones shouting yes. It's a cosmic standoff, and we're all waiting for the tiebreaker. Maybe it'll come tomorrow, maybe in a century, when some clever astronomer catches a quark star in the wild, its quirks laid bare for all to see. Until then, we're left with questions, and that's not a bad place to be. The universe is a treasure chest of riddles, spilling over with wonders we've yet to crack. There's enough out there to keep curious minds busy for generations, assuming we don't lose the spark to chase them. Reflect on that for a moment. The cosmos doesn't hand us answers on a silver platter. It dares us to dig, to dream, to doubt. Quark stars might be figments of imagination, or they might be lurking just beyond our telescopes, winking at us from the dark. Every candidate that flops, every theory that falters is a step closer to the truth. We've been wrong before. Pulsars too fast, diameters too small, and we'll be wrong again. But each stumble sharpens our focus, tunes our instruments, and fuels the fire to keep looking. So, where do we stand? Quark stars are a maybe, a might be, a tantalizing what if that keeps the cosmic conversation alive. They're not confirmed, not dénied, just hovering in the ether, waiting for their moment. And that's the beauty of it. The universe is a vast, wild playground, and we're still kids with magnifying glasses, poking at the unknown. Whether quark stars turn out to be real or just a clever idea, they remind us how much is left to explore. The Big Bang's echoes, the quark's dance, the star's secrets. They're all pieces of a puzzle we're only beginning to assemble. Grab a seat, keep your eyes peeled, and let's see where this cosmic ride takes us next. Theories swirl, but proof? Nada. Most astrophysicists see quark stars as neutron star kin, siblings in the stellar afterlife. But there's a wild card. Edward Witten, a physics luminary, suggests strange matter clumps, Big Bang relics, float out there, possibly as dark matter. A massive star snags one, and instead of a neutron core, a quark star is born. It's a stretch, but it keeps the cosmic pot bubbling. So where are we? Quasi-stars, quark stars. They're shadows on the horizon, waiting to be real or ruled out. The universe is a vast, wild frontier, and we're just dipping our toes in. Every equation, every glimpse nudges us closer or deeper into the unknown. That's the thrill of it. Hang with us, keep gazing up, and who knows? The next breakthrough might be just over the cosmic hill. Picture yourself standing on the edge of a cosmic abyss, peering into the vastness of the universe, where mysteries swirl like stardust in the wind. Among these enigmas are quark stars, elusive hypothetical objects that tantalize scientists and stargazers alike. Whether you buy into the theory or not is up to you. It's a personal call, a bit like choosing your favorite flavor of ice cream. But one thing's undeniable: we don't have a shred of concrete evidence to pin down their existence. Not yet, anyway. Still, the idea of quark stars isn't just some wild flight of fancy. It's a thread that could stitch together the chaotic tapestry of the universe's earliest moments, right after the Big Bang, when everything was a roiling sea of quark matter. And that, my friends, is a fact etched in the cosmic ledger. Why do quark stars matter? Imagine them as time capsules, relics, that could unlock secrets from the dawn of creation. Back then, the youthful universe wasn't filled with the stars and galaxies we know today. It was a hot, dense soup of quarks and gluons, the fundamental building blocks of matter. If quark stars exist, they might offer a glimpse into that primordial chaos, a snapshot of a time when the rules of physics were still being written. It's a tantalizing prospect, one that keeps astronomers up at night, dreaming of the day they might catch one in the act. But so far, these cosmic phantoms remain just out of reach, teasing us from the shadows of theory. Over the years, we've had our hopefuls, candidates that seem like they might fit the quark star bill. Take, for instance, a pulsar in the constellation Ophiuchus, some 39,000 light-years from Earth. This spinning stellar remnant, cloaked in a cryptic catalog number, once dazzled researchers with a jaw-dropping claim. It was clocked at 1,122 rotations per second, making it one of the fastest pulsars ever spotted, a quark star perhaps. The idea sent pulses of excitement through the scientific community. But alas, the thrill was short-lived. Closer scrutiny revealed the numbers didn't hold up, and the object's quark star candidacy fizzled out like a damp firework. Another near miss in the cosmic lottery. Then there was another contender, a neutron star so close to Earth it felt almost neighborly in the grand scheme of things. Early observations painted a curious picture, a tiny diameter, somewhere between 4 and 8 kilometers, and a surface zipping along at 108 kilometers per second. Its temperature? A scorching 700,000 Kelvin, hot enough to make you sweat just thinking about it. Scientists raised their eyebrows. Could this be the real deal? But as they zoomed in, the story shifted. The object turned out to be cooler, closer to 350,000 Kelvin, and a bit chubbier, stretching to 14 kilometers across. Those tweaks flipped the script. Not a quark star, but a garden-variety neutron star. Another swing, another miss. The hunt didn't stop there. In 2008, astronomers turned their telescopes toward a pair of supernovae, wondering if these stellar explosions might conceal quark stars within their fiery hearts. The idea was intoxicating. Imagine a supernova giving birth to something so exotic. Then, in 2015, another supernova caught the spotlight, with whispers that it might be a newborn strange quark star, a rare breed of cosmic oddity. But whispers aren't proof, and despite the buzz, no one's managed to slap a confirmed sticker on these suspects. The evidence cupboard remains stubbornly bare, leaving us with nothing solid to brag about.